Hello, and welcome to The Sleepy Scientist. Tonight, we're drifting into a calm but curious corner of nature, the strange and surprising ways animals sleep. From creatures that nap on the wing to those that barely sleep at all, this is a world full of odd adaptations and quiet mysteries. Before we begin, I'd love to know, where in the world are you listening from tonight? If you enjoy relaxing science stories like this, a gentle nudge to give the video a like and subscribe so you can join us for future explorations. And to those of you already subscribed, thank you. Your support keeps these quiet journeys alive. I'll try not to make this so fascinating that you lie awake, eyes wide, turning over every fact. But if that does happen, at least you'll wake tomorrow with a head full of strange animal trivia. So what does it look like when a creature with no brain falls asleep? Sleep is one of nature's quiet marvels, a state where the body appears to switch off, but the brain hums with its own mysterious rhythms. At its simplest, it can be divided into two main types: rapid eye movement sleep, known as REM, and non-rapid eye movement sleep, or non-REM. In humans, REM is when our most vivid dreams tend to unfold, with the eyes darting beneath closed lids and the brain showing activity patterns almost as lively as when we are awake. Non-REM, on the other hand, is a calmer, slower state, marked by long, deep breaths, steady heartbeats, and waves of electrical activity that ripple gently across the brain. These two states alternate through the night in cycles, like an intricate dance between stillness and activity. In humans, a full cycle lasts roughly 90 minutes, though this is by no means universal. Other animals follow their own tempos, some racing through these stages in mere minutes, others stretching them out for hours. Cats, for example, enter REM much sooner after falling asleep than humans do, while certain marine mammals slip in and out of lighter non-REM states without ever surrendering both halves of their brain at once. At the heart of sleep lies the circadian rhythm, an internal clock that ticks away in almost every living thing, keeping time with the turning of the earth. In humans, this clock is set by a cluster of neurons in the brain called the suprachiasmatic nucleus, which sits just above the point where the optic nerves cross. It uses cues from the outside world, mainly light, to adjust our biological schedule. When daylight fades, the pineal gland begins releasing melatonin, a hormone that nudges the body toward rest. As the morning sun returns, light signals suppress melatonin, encouraging wakefulness. In animals, this process can be similar or wildly different, depending on whether they are nocturnal, diurnal, or active in bursts throughout the day and night. Brain activity during sleep is far from uniform. In non-REM stages, especially the deepest phases, neurons fire in slow, synchronized patterns, like waves rolling onto a shore. This slow-wave sleep is thought to be a time for repair. Muscles recover from strain, the immune system bolsters its defenses, and the brain clears away metabolic waste products. REM, by contrast, is chaotic and vivid. Neurons fire rapidly, brain temperature rises, and certain parts of the brain linked to emotion and memory light up, in patterns that suggest intense internal activity, even though the body is paralyzed from the neck down. This temporary muscle paralysis, known as atonia, prevents dreamers from acting out their visions, a useful safeguard whether you're a human, a dog dreaming of chasing a ball, or a cat deep in an imaginary hunt. What makes this all the more fascinating is how varied these patterns can be across the animal kingdom. Some species spend half their lives in REM, others barely touch it. Certain reptiles have been observed in a state resembling REM, blurring the once neat line between higher mammals and everyone else. And then there are the cephalopods, such as octopuses, which appear to enter a colourful, twitching rest phase that might just be their own version of dream sleep. In every case, sleep is more than just rest. It is a shifting tapestry of electrical signals, hormones, and body rhythms, each stage with its own role to play. Like the slow breathing of the ocean tide, brain waves ebb and flow, carrying the sleeper through deep stillness and into the vivid theatre of REM before returning again. For all its familiarity, sleep remains a vast and largely uncharted territory, one that every creature navigates in its own way. Sleep is one of life's most familiar experiences, and yet its workings are anything but simple. When we close our eyes, our bodies enter a sequence of shifting states that follow a rhythm as old as our species. Broadly speaking, sleep can be divided into two main categories: rapid eye movement, or REM sleep, and non-rapid eye movement, or non-REM sleep. These are not just arbitrary labels, they describe two very different worlds within the mind. Non-REM sleep tends to come first. In its lighter stages, the body relaxes, the heartbeat slows, and breathing becomes steady. Muscles are still capable of movement, and the mind drifts toward quiet thought rather than vivid dreaming. As we slip into deeper non-REM stages, the brain's electrical activity slows and synchronizes, producing the large, sweeping waves that give slow-wave sleep its name. This is a time of physical restoration, when the body directs its energy toward repairing tissues, producing growth hormones, and bolstering the immune system. REM sleep, by contrast, is a lively stage where the brain behaves almost as if it were awake. The eyes dart back and forth beneath closed lids, the heartbeat quickens, and breathing becomes less regular. Most strikingly, the body's voluntary muscles are paralyzed in a state known as atonia, a safeguard that prevents sleepers from acting out their dreams. It is in REM that our most vivid and bizarre dreamscapes tend to unfold, though other animals experience their own versions of this mental theatre. Brain scans show that regions involved in memory, learning, and emotion light up during this stage, suggesting that REM plays an important role in processing the events of the day. The alternation between non-REM and REM forms what is known as a sleep cycle. In humans, each cycle lasts about 90 minutes, repeating several times through the night. Other animals follow very different schedules. A cat, for instance, may fall into REM within minutes of closing its eyes, while some marine mammals cycle through stages in a way that allows them to keep part of the brain awake. These variations hint at sleep's flexibility. The core process is ancient, but its timing and expression adapt to each species' needs. Underlying this dance between states is the circadian rhythm, our internal timekeeper. In humans, this clock is governed by a cluster of neurons in the brain called the suprachiasmatic nucleus, which sits just above where the optic nerves cross. Light is its metronome. When daylight fades, signals are sent to the pineal gland to release melatonin, a hormone that nudges the body toward rest. With morning light, melatonin production drops, paving the way for wakefulness. This cycle is not unique to humans. Almost every organism on Earth has some form of daily rhythm, from flowers that open at sunrise to nocturnal animals that become active as the sun goes down. In many creatures, circadian rhythms are tightly linked to environmental cues beyond light. The tidal rhythms of coastal animals, the temperature shifts that guide desert species, and even the seasonal patterns of migration and reproduction all feed into the body's timing mechanisms. In the wild, sleep is often less about the clock on the wall and more about synchronizing with the predictable changes in the surrounding world. The brain's electrical patterns during sleep are one of its most fascinating features. In non-REM sleep, especially the deeper stages, neurons fire in slow, regular waves, each surge of activity rolling across the cortex like a gentle swell on the sea. These slow waves are thought to be essential for consolidating certain types of memory and for clearing out waste products that accumulate during wakefulness. In REM sleep, those slow swells give way to rapid, unpredictable bursts of activity, as if the calm ocean has been stirred by sudden gusts of wind. The patterns resemble those of wakefulness, but they are untethered from the senses, producing the vivid, sometimes illogical sequences we know as dreams. While humans are often the default reference point for understanding sleep, other species remind us just how varied these processes can be. Horses and giraffes spend far less time in REM than we do. Some birds have REM phases so brief they seem almost like momentary flickers, while certain reptiles show signs of a REM-like state that challenges the long-held belief that dreaming is exclusive to mammals and birds. In octopuses, a colourful twitching rest phase appears to be a form of REM, complete with rapid changes in skin pattern and texture. What all these examples share is a core pattern of alternating activity and rest within the brain, a rhythm that seems to serve both body and mind. Whether it is in the slow, steady waves of deep non-REM sleep or the quick, chaotic bursts of REM, the sleeping brain is far from idle. It is busy tuning itself, consolidating memories, repairing cells, and perhaps weaving dreams. Like the slow breathing of the ocean tide, brain waves ebb and flow, carrying each sleeper, human or animal, through the night's intricate and essential cycles. Why we sleep is a question that has puzzled scientists for centuries. At first glance, it might seem like an odd evolutionary choice. In the wild, spending hours each day lying still, unaware of your surroundings, sounds like the worst possible survival strategy. Yet almost every animal on Earth sleeps in some form, from humans and whales to tiny insects and creatures without brains. Sleep, it seems, must be doing something so vital that no species has been able to do without it. One of the most straightforward explanations is the energy conservation theory. Sleep reduces the body's demand for fuel at times when it is less efficient or more dangerous to search for it. In humans and many other animals, body temperature drops slightly during rest, metabolism slows, and energy is used at a reduced rate. For early creatures, sleeping during the coldest, darkest hours meant burning fewer calories while avoiding the hazards of moving through a world they could not see well. Even today, this daily dip in metabolic rate suggests that sleep is an effective way of saving resources, a built-in strategy to waste less when activity is unlikely to pay off. But the benefits of sleep go well beyond saving energy. One of its most powerful roles lies in memory consolidation and learning. During certain stages of sleep, especially in REM and deep non-REM, the brain appears to replay and organize the day's experiences. In laboratory experiments, rats trained to run mazes show brain activity during sleep that mirrors the same patterns recorded while navigating the maze earlier. It is as if the brain is quietly rehearsing the task, strengthening the neural connections needed to remember it. Birds offer another compelling example. Songbirds practice their tunes during the day, and then, during sleep, their brains fire in patterns that suggest they are refining and polishing their songs. Without adequate rest, learning slows, and memories become less reliable, a truth shared across mammals, birds, and possibly even some reptiles. Sleep is also a time for cellular repair and immune system maintenance. Deep non-REM sleep is when the body releases growth hormone, which helps repair tissues and muscles. It is also when the immune system steps up production of certain proteins that fight infection and inflammation. In recent years, scientists have discovered that the brain has its own cleaning crew, the glymphatic system. This network of channels flushes out waste products that build up during wakefulness, including proteins linked to diseases like Alzheimer's. The glymphatic system is far more active during deep sleep, suggesting that without rest, the brain's housekeeping slows to a crawl, potentially allowing harmful substances to accumulate. Of course, in the wild, there is a trade-off between the benefits of sleep and the risks it brings. Predator avoidance theories suggest that the timing, depth, and duration of sleep are shaped by an animal's need to stay alive. Prey animals tend to sleep less deeply or in shorter bursts, keeping their senses ready for danger. Grazing species like deer and horses rarely fall into long stretches of deep sleep, instead taking many short naps spread throughout the day and night. Predators, on the other hand, often enjoy longer, deeper sleep because they face fewer threats while resting. Lions can spend over 20 hours a day sleeping when food is plentiful. For both predators and prey, the key is to balance the restorative benefits of sleep with the constant need for vigilance. To understand where sleep came from, we have to look deep into evolutionary history, and surprisingly, the trail might lead to creatures without brains at all. Some species of jellyfish, such as Cassiopeia, the upside-down jellyfish, show clear signs of a sleep-like state. At night, they pulse their bell-shaped bodies less often and respond more slowly to disturbances. When researchers kept them active during their usual rest periods, the jellyfish became sluggish and less responsive the next day, suggesting that even they need recovery time. This is remarkable because jellyfish have no central brain, only a simple nerve net. The fact that jellyfish, animals that split from the branch leading to most other animals hundreds of millions of years ago, seem to sleep suggests that rest is not an invention of complex nervous systems. Instead, it might be one of the most ancient behaviours in the animal kingdom, emerging in early multicellular life as a way to coordinate activity with environmental cycles. Over time, as nervous systems became more complex, this simple rest evolved into the multi-stage, highly organised sleep we see in mammals, birds and other advanced species. Sleep may never have had a single purpose. Instead, it seems to be a collection of essential processes, all bundled into one behaviour. It conserves energy when activity would be wasteful. It strengthens the mind's ability to learn and remember. It repairs the body's tissues and boosts defences. It reduces risk by matching rest to safer periods. And it has roots so deep in our evolutionary past that even brainless animals take part. Far from being an inconvenience or a vulnerability, sleep is one of life's most enduring and essential rhythms, a nightly reminder that sometimes the best way to survive is to be still. For most of us, sleep is an all-or-nothing affair. We lie down, close both eyes, and let the whole brain drift away together. But in the open ocean, in high mountain skies, and along the edges of windswept lakes, some animals have perfected a trick that seems almost magical. They sleep with only half their brain at a time. The other half stays awake, alert, and ready for action. This unusual ability is called Unihemispheric slow-wave sleep, and it is the ocean's version of sleeping with one eye on the kids, except the kids might be hungry sharks, rival pods, or stormy weather. The most famous masters of this technique are dolphins. Unlike humans, they cannot rely on an unconscious breathing reflex to keep them alive at night. Every breath is a deliberate choice, and in the ocean, forgetting to surface would be fatal. Unihemispheric slow-wave sleep solves that problem perfectly. When the left hemisphere of the brain sleeps, the right hemisphere remains alert enough to keep the dolphin swimming slowly and rising to the surface at regular intervals. The right eye, connected to the left hemisphere, stays closed, while the left eye, connected to the awake hemisphere, remains open, scanning the water for obstacles or threats. After a while, the two hemispheres trade places, so that each gets its share of deep rest without ever letting the body go fully offline. Whales use the same approach, though the scale is different. Some species, like sperm whales, can rest vertically, their massive bodies hanging motionless in the water column, like pillars in a blue cathedral. Others float just below the surface in a behaviour called logging, because they resemble drifting tree trunks. In both cases, one brain hemisphere remains on duty to manage breathing and awareness, while the other sinks into the slow, synchronized brainwaves of deep sleep. For calves, life is even more dynamic. Young whales and dolphins need to breathe more often and stay close to their mothers, so mothers swim continuously during the early weeks, guiding their calves through a kind of rolling shared wakefulness, where neither is ever completely at rest. These skies hold their own half-brain sleepers. Migratory birds, such as the great frigate bird, spend days or even weeks in the air without landing. These birds can sleep while gliding, using air currents and subtle wing adjustments to stay aloft. During flight, they dip into brief bouts of unihemispheric slow-wave sleep, often lasting only seconds at a time, but enough to keep the brain functioning during long journeys. One hemisphere rests while the other monitors balance, navigation, and the surrounding airspace. The open eye on the awake side keeps watch for companions, weather changes, or distant land. On the ground, unihemispheric sleep appears in birds that roost in groups. Ducks resting in a line often show a neat arrangement. Those in the middle close both eyes, while those on the ends keep the outward-facing eye open. The next time the group shifts, the pattern changes and new sentinels take up the watch. It is a low-tech but highly effective security system built into the very wiring of the brain. The mechanics behind this behaviour are as fascinating as the behaviour itself. In all vertebrate brains, the left and right hemispheres are connected by bundles of nerve fibres, allowing constant communication. In species capable of unihemispheric sleep, these hemispheres can operate more independently, each controlling the opposite eye and its half of the body. When one hemisphere enters slow-wave sleep, its neurons fire in large synchronized waves, while the awake hemisphere continues with the faster, more irregular patterns of wakefulness. Muscle tone remains intact because this is not REM sleep. There is no dream paralysis here. The awake side keeps swimming, gliding, or standing guard while the resting side repairs itself. The open eye is not just a quirk, it is a vital part of the system. Because visual signals cross over to the opposite hemisphere, the open eye belongs to the hemisphere that is awake, feeding it information about the environment. In dolphins, the open eye often faces the rest of the pod, allowing social contact to continue even in partial sleep. In birds, the open eye usually points outward, keeping watch for predators. This is sleep stripped down to its most efficient form, resting without ever becoming oblivious. Why would such a strange arrangement evolve? In the case of marine mammals, it is easy to see the advantages. Breathing must be actively managed, and the ocean is full of potential hazards. A fully unconscious whale could sink too deep, drift into dangerous waters, or fail to notice a predator. By sleeping in a shift between hemispheres, these animals never lose the ability to respond. For migratory birds, the pressure is different but just as intense. Long flights across open ocean or over inhospitable terrain leave no safe place to land. Sleeping while flying, even for brief moments, allows the brain to rest without cutting the journey short. For flocking birds and shoreline species, keeping an eye open at the edge of a group gives advance warning of approaching predators, increasing the survival chances of the whole group. The fact that this behaviour appears in animals as different as dolphins, whales, seals, ducks, and frigate birds suggests that it has evolved multiple times, shaped by similar pressures in very different environments. This is a classic case of convergent evolution, when nature, faced with the same problem, comes up with the same solution in separate lineages. Whether in air or water, the challenge is the same: how to rest without becoming an easy target. Even some seals show a remarkable twist on the system. Fur seals, for example, sleep with one hemisphere at a time while at sea, but when they haul out on land, they can enjoy full bilateral sleep like a typical mammal. This switchable system shows just how adaptable sleep can be when the environment changes. For humans, unihemispheric sleep is more of a curiosity than a possibility. We are wired for both hemispheres to sleep together, and while there is some evidence that we may sleep more lightly in a new or unfamiliar environment, a kind of partial night watch. It is nothing like the finely tuned system in these animals. For us, the safest place to sleep is somewhere secure enough to shut down completely. For a dolphin or a migratory bird, safety comes from never shutting down entirely. Unihemispheric slow-wave sleep challenges our idea of what sleep really is. It is not a single, uniform state, but a flexible set of strategies. In some animals, it can be split neatly between the brain's hemispheres, turning rest into a carefully balanced negotiation between vulnerability and vigilance. In the hush of a moonlit ocean, or the thin blue air high above the waves, half a mind drifts in slow, rolling waves, while the other half keeps the body steady, the senses sharp and the journey moving forward. It is a reminder that in nature, even something as universal as sleep can take unexpected forms. For some animals, being half asleep is not a sign of restlessness, but of perfect adaptation, proof that sometimes the best way to survive the night is to never fully leave it. For most of us, a nap means at least a few minutes of peaceful dozing, preferably on something soft and horizontal. In the animal kingdom, however, a nap can be over almost before it begins. Some species have perfected the art of sleeping in tiny installments, mere seconds at a time, without losing their grip on survival. These are the masters of the micronap, and their schedules make even the busiest humans seem like a chronic oversleeper. One of the most astonishing examples comes from birds that travel for days without landing. The great frigate bird is a champion of long-distance flight, spending weeks over the open ocean where there is nowhere to perch. Researchers fitted these birds with tiny brainwave recorders and discovered that they grab sleep in incredibly short bursts mid-flight, sometimes only a few seconds long. In these moments, one hemisphere of the brain slips into slow-wave sleep, or both hemispheres rest together briefly if conditions are calm. The bird's wings stay locked in a gliding position, riding air currents while the brain snatches a lightning-fast moment of rest. It is not a luxurious slumber, but it is enough to keep the bird functioning across thousands of kilometers of sky. Closer to shore, other birds also employ micronapping as a survival strategy. Swifts, for instance, are known to spend months on the wing, and while the exact details of their sleep patterns are still being studied, it is thought that they too rely on short strategic naps while airborne. In both cases, the secret is efficiency, no full landings, no prolonged vulnerability, just small doses of rest slotted into the rhythm of movement. The water holds its own specialists in brief, scattered sleep. Seals and sea lions, for example, have complex sleeping habits that change depending on whether they are on land or in the sea. On land, they can sleep more like typical mammals, enjoying longer, deeper stretches. In the water, however, things are different. Some seals will float vertically with their noses just above the surface, allowing them to breathe without waking fully. Others alternate between short naps while drifting and brief periods of alertness to swim or avoid predators. These aquatic naps can be just a few minutes long and are sometimes broken into even smaller fragments, especially in rough seas or crowded waters. Sea lions show similar flexibility, catching sleep in bursts while bobbing at the surface or resting in shallow water. The question is why such fleeting moments of rest work so well. For animals living in high-risk or high-demand environments, micro-napping can actually be more practical than long stretches of uninterrupted sleep. By sleeping in many short bouts, an animal can maintain a near constant level of awareness and readiness. It is a way of balancing two conflicting needs: the brain's demand for rest and the body's need to stay alert. A bird in flight cannot afford to be unconscious for long without risking collision, drift, or disorientation. A seal in open water cannot remain unaware for hours without becoming an easy target. In both cases, micronaps offer the smallest possible window of vulnerability while still providing the brain with recovery time. It also turns out that sleep is surprisingly adaptable. While humans tend to experience benefits from consolidated rest, many animals can reap similar rewards from fragmented sleep spread out across the day and night. The key seems to be that over time, the total amount of slow-wave and REM-like sleep adds up to what the animal needs. Instead of a solid block, it is a mosaic of moments, each one replenishing a fraction of the brain's energy and function. Studying such tiny sleep episodes is no easy task. Scientists use a combination of tools to measure them, the most important being electroencephalography, or EEG, which records electrical activity in the brain. For wild animals, this often involves developing lightweight, waterproof, and sometimes even aerodynamic equipment that can be attached without affecting natural behavior. In the case of frigate birds, researchers used miniature EEG devices paired with GPS trackers to monitor both brain activity and flight paths. For seals and sea lions, similar devices have been used alongside depth sensors to see how sleep changes with diving and surfacing. The resulting data is astonishing. Brainwave patterns can reveal that an animal was asleep for just a few seconds before waking again to navigate or adjust its body. Motion sensors also play a role, particularly for animals in flight. By tracking wing beats, gliding angles, and body movements, scientists can match moments of minimal motion with signs of sleep in the brain. For marine mammals, depth and position logs help show whether a nap happened while drifting, floating, or actively swimming. The combination of brain data and physical movement provides a fuller picture of just how animals can function with such fragmented rest. These findings challenge the idea that long, deep sleep is the only path to recovery. In the world of micronaps, survival depends on making the most of seconds, not hours. A frigate bird gliding above endless waves, a swift slicing through the evening air, a seal bobbing gently in the swell. Each is proof that rest does not have to come in one unbroken stretch to work. In environments where danger never sleeps and the journey never pauses, the ability to take sleep in small, perfectly timed sips can be the difference between thriving and falling behind. Far from being a compromise, micronapping is a refined adaptation, a reminder that nature often solves problems with elegant efficiency. Where we see exhaustion, these animals see opportunity, taking the briefest moments to restore themselves before moving on again. It is sleep stripped down to its most essential form, quick, precise, and just enough to keep the mind sharp and the body strong. Dreaming is one of the most mysterious experiences of sleep, a private theatre in which the mind plays scenes without an audience. In humans, it is most vivid during rapid eye movement sleep, or REM, when the brain's electrical activity surges into patterns not far removed from wakefulness. But dreams are not ours alone. Across the animal kingdom, many species enter REM, and while we cannot ask them what they saw in their minds, their bodies, and sometimes their colours, offer intriguing clues. In mammals, REM sleep is widespread, though the amount varies enormously. Humans and other primates spend a significant fraction of their sleep in this stage, as do cats, whose twitching paws and flicking ears betray busy dream worlds. Dogs also show telltale signs, soft yips, paddling legs, and rapid eye movements that suggest the replay of daily adventures. Laboratory EEG recordings from dogs reveal brain patterns during REM strikingly similar to those seen when awake, especially in regions tied to movement and perception. In rats, the connection between experience and dream activity is even clearer. Studies have shown that rats trained to navigate a maze will display the same neural firing sequences during REM as when they were running the maze earlier. It is as if the brain is rehearsing the route in sleep, reinforcing the memory for the future. Birds too experience REM, though in much shorter bursts. A pigeon's REM phase may last only a few seconds, yet during that time its eyes may flutter and its head shift slightly, hinting at an internal scene playing out. Songbirds provide some of the most compelling avian evidence. Zebra finches, for example, exhibit neural activity during sleep that mirrors the precise patterns used to sing their songs when awake. This has led researchers to suspect that birds may practice their melodies in dreams, fine-tuning their performance without making a sound. Reptiles were once thought to miss out on REM entirely, but recent research has challenged that assumption. Studies on Australian dragons, a type of lizard, revealed two alternating sleep states, one of which shares key characteristics with REM. This suggests that dreaming, or at least a REM-like process, might be far older in evolutionary terms than once believed, perhaps stretching back hundreds of millions of years. In the ocean, the story takes on even more colour. Cephalopods like octopuses and cuttlefish appear to go through active sleep phases, during which their skin patterns shift in rapid, complex sequences. One moment they are pale, the next patterned with bold stripes or mottled spots, as if reacting to unseen surroundings. Some scientists speculate these changes could reflect dream imagery, perhaps a remembered hunt, a passing predator, or the shifting light of their coral reef homes. While we cannot know for certain, the synchrony between skin pattern shifts and body movements in these resting cephalopods makes the possibility tantalizing. Speculating about what animals dream is an exercise in imagination, but one that can be grounded in behaviour. A dog lying curled on the carpet may be back in a sunlit field, nose to the ground, following the invisible trail of a rabbit. The twitch of a paw could be the leap to give chase. A songbird in REM might be high in the early morning canopy, weaving its notes into a perfect sequence. A rat may be retracing the twists of a familiar tunnel, the memory sharpened with each silent rehearsal. An octopus could be gliding over a seabed dotted with shells, the colours in its skin pulsing to match the imagined textures and shadows. Its arms might curl slightly in response to dream prey, the whole body shifting through patterns only it can see. Even without human-style consciousness, the mechanics of REM, rapid neural firing, vivid sensory activation, and bodily signs of engagement, suggest that animals are not simply resting, but inhabiting an inner space where past and present blur. Why animals dream remains an open question. One idea is that REM serves as a neural training ground, allowing the brain to run simulations of real-life challenges. For a predator, this might mean refining hunting skills. For prey, rehearsing the recognition and escape from danger. Another theory is that dreams help integrate and store new memories, strengthening the recall of important experiences and discarding what is less useful. In both cases, REM is not idle time. It is an active process of mental maintenance, shaped by evolution to keep the mind sharp. The diversity of dreaming across species hints at its deep evolutionary roots. The presence of REM-like states in mammals, birds, reptiles, and even invertebrates like cephalopods suggests that some form of active, internally driven sleep arose long ago and has been preserved because it offers clear advantages. Whether those advantages lie in memory, learning, problem-solving, or emotional regulation, they have proved valuable enough to survive in creatures as different as a finch and an octopus. In the end, the dreams of animals remain private worlds, glimpsed only in fragments, a twitch here, a flutter there, a sudden shift of colour. Yet these fragments suggest something universal, that life, in all its forms, needs time not only to rest the body but also to wander the landscapes of the mind. In those quiet hours, paws run without touching the ground, wings beat without lifting into the air, and skin flashes patterns to a sea that exists only in memory. The sleeper is still, but the dream goes on, as real to the brain as any waking moment. In the human world, someone getting less than 4 hours of sleep is considered severely sleep-deprived. Yet in the animal kingdom, there are creatures that thrive on a fraction of that. Not for a few days, but for their entire lives. These are the almost sleepless, animals that seem to make a living out of doing more with less. Giraffes are perhaps the most extreme example. Early field studies once suggested that they hardly slept at all, and even with more precise modern observations, their total rest time still averages between just 30 minutes and 2 hours in a full day. Most of this comes in short bursts of a few minutes, often taken while standing. Occasionally a giraffe will fold its long legs under its body, curl its neck back, and rest its head on its hip in a position that looks both awkward and strangely graceful. These rare deep sleep episodes are brief, sometimes lasting only a few minutes before the animal is up and alert again. Living in open grasslands with few hiding spots and plenty of large predators, it makes sense that giraffes would sacrifice comfort and duration for constant vigilance. Elephants are similarly frugal with their sleep. In the wild, African elephants average about 2 hours of rest each day, and sometimes go without any measurable sleep at all for short periods. They tend to rest standing with deep sleep, including REM, occurring when they lie down, which happens infrequently. Their long migrations need to find food, and the ever-present threat of predators make long, uninterrupted rest impractical. In fact, elephants hold the record for the shortest daily sleep of any mammal studied to date. Migratory birds also demonstrate remarkable flexibility with their sleep needs, particularly during long flights. The great frigate bird, for example, can travel for weeks without landing, cutting its daily sleep to a fraction of what it gets on land. In the air, these birds rely on very short bouts of unihemispheric sleep, resting one side of the brain at a time while continuing to glide. Some other migratory species may drastically reduce both REM and non-REM sleep during long journeys, making up for the loss once they reach their destination. This ability to temporarily slash sleep without apparent harm is a rare and valuable adaptation in the animal world. The obvious question is how these animals avoid the harmful effects of such limited rest. In humans, chronic sleep deprivation affects memory, immune function, and even basic physical coordination. For giraffes, elephants, and migratory birds, the answer likely lies in how they structure the sleep they do get. Their rest tends to be highly efficient, packing in the most restorative stages into short, consolidated episodes. In other words, while the total hours are low, the quality of sleep may be exceptionally high. There may also be differences at the cellular and neurological level. Some studies suggest that parts of the brain can nap independently during waking hours, entering brief moments of slow-wave activity without the whole brain going offline. This kind of localized rest could allow these animals to recover gradually throughout the day, rather than relying entirely on a single block of consolidated sleep. Energy use is another factor. Giraffes and elephants both have slow metabolic rates relative to their size, which may reduce the physiological pressure to sleep for long periods. Large body size also deters many predators, meaning that these animals can afford to sleep lightly without needing the deep, prolonged rest smaller prey might require for recovery. For migratory birds, sleep reduction is a temporary strategy, a calculated trade-off that allows them to cover vast distances at the cost of deferring some maintenance tasks until they are safely grounded. In all cases, the pattern reflects an adaptation to life's demands. In environments where constant movement, predator awareness, or migration are more important than prolonged rest, nature has shifted the balance. The result is a set of animals that challenge our assumptions about how much sleep is truly necessary. For them, rest is not an 8-hour block but a flexible resource, taken in short, potent doses and, when needed, deferred until conditions are right. These almost sleepless species are a reminder that there is no single rule for how much sleep life requires. For some, the night is a long, luxurious stretch of rest. For others, it is a series of fleeting moments, each one enough to keep the mind sharp, the body ready, and life moving forward. Sleep for most creatures is a time of stillness, a retreat from movement and noise. But for some animals, stopping entirely is simply not an option. Their survival depends on constant motion, whether to keep breathing, to stay balanced in the air, or to remain safe from predators. Over millions of years, evolution has crafted a remarkable solution: the ability to rest without halting, to let part of the brain sleep while the body keeps moving. Dolphins are perhaps the best-known masters of this skill. As voluntary breathers, they cannot rely on an automatic system to keep air flowing into their lungs. Every breath must be consciously taken, which makes complete unconsciousness impossible. Their answer is Unihemispheric slow-wave sleep, a state where one hemisphere of the brain slips into deep rest, while the other stays alert enough to guide slow, deliberate swimming. The eye connected to the sleeping hemisphere closes, while the other remains open, keeping watch for predators, obstacles, and companions. After a period of time, the hemispheres swap roles, ensuring each half gets its turn to recover. A dolphin in this state is a picture of controlled calm. It moves in slow arcs or gentle lines, breaking the surface at regular intervals to breathe before sinking quietly beneath the waves. Because slow-wave sleep does not trigger the muscle paralysis seen in REM sleep, the body retains enough tone to swim with minimal effort. Dolphin calves, who must breathe more frequently, complicate things further. Mothers will swim almost constantly in the first weeks after birth, both to help the calf keep pace and to protect it from predators. By alternating which hemisphere of the brain is asleep, mother and calf can remain in motion without missing the rest they need. High above the ocean, another traveller faces the challenge of sleeping in motion. Great frigate birds are masters of soaring flight, their long, narrow wings carrying them over vast stretches of sea for days or even weeks at a time. There are few safe places to land during these journeys, so the birds have learned to rest while airborne. They take their sleep in short bursts, sometimes closing down one hemisphere at a time and occasionally letting both hemispheres rest for just a few seconds while gliding on stable air currents. An open eye on the alert side keeps track of other birds, changes in wind, and signs of land, while the sleeping side dips into deep, slow-wave rhythms. Their bodies are built for this. Wings that lock into place reduce the need for active muscle control, letting them ride the air with minimal effort. In the deep, some sharks must also find ways to rest without stopping. Certain species, such as the great white, rely on a constant flow of water over their gills to extract oxygen. Stopping completely would reduce this flow and threaten their survival. Instead, they enter a reduced activity state, where the brain's responsiveness drops, but basic motor circuits keep the body swimming in slow, steady patterns. In areas with strong currents, some sharks can even rest more passively, positioning themselves so the water moves over their gills without as much effort. In each of these examples, the mechanics of movement during partial sleep are shaped by the animal's needs. In dolphins, the awake hemisphere sends steady, precise commands to the swimming muscles. In birds, the combination of wing structure and gliding behavior means the awake side of the brain only needs to make occasional adjustments. In sharks, spinal reflexes and autonomous neural circuits handle repetitive swimming motions without requiring much from the higher brain. The benefits go far beyond convenience. In the open ocean, stillness can make an animal vulnerable to predators, dangerous currents, or sudden environmental changes. For birds flying across the sea, the inability to land means every moment must be managed carefully to avoid exhaustion. By blending motion with rest, these animals reduce risk while still recovering their mental and physical strength. This style of sleeping also shows how flexible the very concept of rest can be. Humans might stir in the night or turn over in bed, but such movement is secondary to the main goal of stillness. For dolphins, frigate birds, and certain sharks, movement is the foundation, and sleep is woven around it. They operate in a careful balance where part of the brain is tuned to the environment, while the rest slips into recovery mode. In the quiet, slow swimming of a dolphin under a starlit sky, in the long glide of a frigate bird on an invisible current, or in the steady, unhurried passage of a shark through dark water, there is a rhythm that never truly stops. These creatures rest without surrendering their place in the world, drifting between wakefulness and slumber in a way that seems almost effortless. For them, the journey never pauses. Only the mind does, one side at a time. Sleep does not always happen in a bed, or even in what we might consider a comfortable position. Across the animal kingdom, countless species have found ways to rest in positions that appear awkward, unstable, or downright impossible to the human eye. For them, these positions are not only natural but often serve a purpose beyond comfort. Flamingos are perhaps the most famous example of a curious sleeping posture. They often rest, and sometimes even sleep, while balancing on a single leg, the other tucked neatly beneath their body. It might seem like a precarious balancing act, but flamingos can maintain this stance with a little effort. Studies have shown that their joints can lock into place, allowing them to remain upright without active muscle engagement. The reason for this pose is still debated, but one leading theory involves thermoregulation. By tucking one leg up against their body, they reduce heat loss to the water they often stand in. Alternating legs helps to minimize fatigue and keep both limbs warm. What looks like a delicate balancing trick may actually be a way to conserve energy, while staying ready to react to predators. Bats take a more extreme approach to gravity, resting and sleeping while hanging upside down. This position is not a strain for them because their anatomy is built for it. In their feet, a special tendon locking mechanism allows them to hang without using any muscular effort. When a bat's body weight pulls down, the tendons automatically tighten, causing their claws to grip whatever surface they are attached to. Even in death, a bat can remain hanging until something disturbs the grip. This upside-down position offers several advantages. It keeps them hidden from predators, places them close to a takeoff point for flight, and allows them to roost in areas that few other animals can access. Sloths add another variation to unusual sleeping positions. They spend much of their lives hanging from tree branches, using strong curved claws to hook securely into the wood. Their muscles and tendons allow them to hang effortlessly for hours, even while asleep. Sloths may sleep curled against the trunk draped over a branch, or suspended completely upside down. Their slow metabolism and low energy needs mean they can stay in these positions for long stretches without discomfort. From a predator's perspective, their stillness and camouflage make them difficult to detect. From a human perspective, they appear to be in a constant state of relaxation, even when their chosen resting spot is several meters above the ground. Owls and many other birds use yet another distinctive position for rest. It is common to see them with their heads turned backwards, tucked under their wings. This position might look awkward, but for birds it is both comfortable and functional. The twisting of the neck allows them to bury their beaks into soft feathers, reducing heat loss from the head. Birds also have a tendon-locking system in their legs and feet, similar to bats, which keeps them securely perched without expending energy. This means they can sleep standing up on a branch without fear of falling, even during gusts of wind. The head-tucked posture also keeps their vulnerable eyes and beak protected while they rest. These extreme sleeping positions are often a combination of evolutionary adaptation and practical necessity. For flamingos, standing on one leg reduces heat loss and may even deter some parasites in the water. For bats, hanging upside down is both a shelter and a launch pad. For sloths, an inverted or draped position is the safest way to stay hidden in the canopy. For owls, the tucked head posture provides warmth, security, and energy conservation all at once. In each case, the posture itself has been shaped by countless generations of trial and error in the natural world. Animals that could rest securely, conserve energy, and remain ready to respond to threats were the ones more likely to survive. Over time, these positions became fixed parts of their biology, supported by anatomical features that make them sustainable. The human body is simply not designed for most of these poses. Our muscles tire too quickly, our joints lack the locking mechanisms, and our balance depends too much on constant micro-adjustments. Watching a flamingo balance effortlessly, a bat hanging in silent clusters, a sloth suspended in leafy stillness, or an owl sleeping with its head completely hidden, can feel like a glimpse into a different set of physical rules. For these animals, gravity, balance, and rest have merged into something entirely their own. They sleep not in defiance of their environment, but in perfect harmony with it, using their bodies in ways that seem strange to us, but feel as natural to them as lying down does to us. Seasonal sleep is one of nature's most ingenious survival strategies. In parts of the world where food becomes scarce and temperatures plummet, some animals slip into a special state that allows them to ride out the harshest months with minimal energy use. This can take the form of hibernation or torpor, two terms often used interchangeably, but in reality they are quite different in scale and purpose. Hibernation is a long-term state of dramatically reduced metabolic activity, lasting weeks or even months. Animals in true hibernation lower their body temperature close to the surrounding environment, slow their heart rate to a fraction of its normal pace, and drastically reduce breathing. It is not the same as deep sleep. In fact, it is more like controlled, temporary shutdown. Torpor, on the other hand, is shorter and shallower. An animal in torpor might enter this state overnight or for a few days, using it as a quick energy-saving measure without the full commitment of hibernation. Bears are the most famous hibernators in popular imagination, yet what they do is technically more like a prolonged form of torpor. Their body temperature drops only a few degrees rather than plunging to near-freezing levels, and they remain capable of waking quickly if disturbed. This makes sense for a large predator that may need to defend itself or take advantage of unexpected opportunities for food. During this period, bears survive entirely on fat reserves, recycling waste products in their bodies to avoid the damage that prolonged inactivity would cause in other animals. Ground squirrels, in contrast, are true hibernators. As winter sets in, their body temperature can fall close to the temperature of the burrow, sometimes just above freezing. Their heartbeats slow from hundreds per minute to only a few dozen, and breathing becomes barely detectable. Periodically, they will rouse slightly, perhaps to adjust their position, urinate, or briefly eat stored food, but for the most part they remain in this suspended state until the environment warms again. Then there are hummingbirds, who use torpor on a nightly basis rather than seasonally. With metabolisms that run at extraordinary speeds, these tiny birds need to eat almost constantly during the day just to survive. At night, without food, their energy needs could overwhelm them. Torpor allows them to slow their metabolism drastically, reduce their body temperature, and conserve enough energy to make it through until morning. For a hummingbird, this nightly drop into torpor can mean the difference between life and death. A key feature of both hibernation and torpor is the metabolic slowdown. In true hibernators, this can mean consuming only a tiny fraction of the energy they would need when active. Oxygen use drops sharply, and in many cases blood flow is restricted to only the most vital organs. In animals like ground squirrels, enzymes in the body are specially adapted to work efficiently, even at these low temperatures, avoiding the damage that cold can cause to proteins and tissues. Body temperature control is one of the most important aspects of seasonal sleep. In hibernators, the drop can be dramatic. Some ground squirrels can survive with body temperatures just above freezing for weeks at a time. In torpid animals, the drop is much less extreme, providing a balance between energy savings and readiness to wake quickly if needed. This difference is why a bear can be roused from its den by a sudden disturbance, while a true hibernator would take far longer to return to full alertness. The idea that animals sleep through winter is one of the most persistent myths in wildlife biology. Hibernation is not a long, uninterrupted nap. In many species, animals cycle through different depths of torpor, occasionally waking to drink, groom, adjust their position, or even leave the den briefly. The difference is that during the hibernation period, their overall activity and energy demands are drastically reduced, allowing them to survive without constant access to food. Seasonal sleep strategies are not limited to cold climates. In desert environments, some species enter a similar state during periods of extreme heat and drought, a behavior called estivation. Like hibernation, it involves slowing metabolism and conserving energy, but the trigger is a lack of water rather than freezing temperatures. This shows just how adaptable the principle of seasonal sleep can be. It is less about winter and more about surviving environmental extremes of any kind. Whether it is a bear in its den, a ground squirrel curled in an underground chamber, or a hummingbird perched on a branch in the stillness of night, seasonal sleep represents a finely tuned balance between energy conservation and survival. It is not laziness, and it is not simply sleep in the human sense. It is a carefully evolved physiological tool, one that allows life to endure when the world outside is at its most hostile. For animals that live entirely or mostly beneath the surface, sleeping is a challenge that requires balancing safety, oxygen intake, and buoyancy. The underwater world never truly stops. Currents keep moving, predators keep hunting, and oxygen can be limited. Yet even here, creatures find ways to rest. What counts as sleep for a fish or an amphibian is often far removed from our own nightly rituals, but the basic need for downtime is just as strong. One of the first differences to understand is that most fish lack eyelids. This means they cannot close their eyes, which makes the concept of looking asleep difficult for us to picture. Instead of shutting out the world visually, many fish enter a state of reduced activity and slower metabolism. Their fins may stop moving except for the occasional gentle flick to maintain balance, and their responsiveness to external stimuli drops. Some even change colour slightly, a phenomenon linked to shifts in skin pigmentation during rest. Resting strategies in fish vary widely depending on habitat and lifestyle. Reef fish often find a sheltered nook in coral or rock crevices, where they can stay relatively still and hidden. Parrotfish famously secrete a mucus cocoon around themselves before sleeping, which may mask their scent from predators and protect them from parasites. In open water, where there is no convenient shelter, some species hover in place, relying on subtle adjustments of their fins to maintain position. Others drift with slow currents, conserving energy while allowing the water to carry them. Amphibians, which split their lives between water and land, have more varied resting habits. Frogs and toads may sleep underwater, on the surface, or on land depending on species and temperature. Aquatic frogs tend to rest at the bottom or among plants, coming up for air periodically. Some salamanders do much the same, lying motionless under rocks or logs, their slow heartbeat and reduced movement conserving energy. Amphibians are also sensitive to seasonal changes, with many entering deeper states of dormancy during cold or dry periods. Aquatic reptiles like turtles and crocodilians have adapted their own ways of resting in the water. Freshwater turtles can sleep submerged for extended periods, slowing their metabolism so much that oxygen absorbed through the lining of their throat and cloaca is enough to keep them alive. Sea turtles may wedge themselves under coral ledges or inside rock crevices, sometimes staying underwater for several hours at a time. Crocodiles, though far more predatory and alert, still need rest, and they often float almost motionless at the water's surface with eyes and nostrils exposed, or sink to the bottom in shallow areas, entering a light doze. The choice between sleeping in currents or still waters comes down to energy costs and safety. In still waters, it is easier for an animal to remain motionless without expending much energy. This is why many fish and amphibians choose calm lagoons, sheltered bays, or quiet river bends for their resting spots. In contrast, animals sleeping in areas with steady currents must counteract the push of water, which requires more frequent fin or body movements. Some species adapt by finding eddies or areas behind rocks where the current is weaker. Others may use the current to their advantage, resting while drifting slowly along with it, much like a person floating down a lazy river. Oxygen availability plays a major role in how long an aquatic animal can remain at rest. In warm water, oxygen levels are lower, which means animals tire faster and must surface or move more often to breathe. In cold water, oxygen dissolves more readily, and metabolic rates are slower, allowing for longer resting periods. This is why sea turtles in colder regions can sometimes sleep for several hours underwater, while those in warmer tropical waters may only manage a fraction of that time. Fish that rely on constant water flow over their gills, such as many sharks, cannot afford to stop moving entirely. Instead, they enter a form of reduced alertness while maintaining slow, steady swimming to keep oxygen flowing through their gills. The mechanics of underwater sleep are a fine-tuned balance between vulnerability and survival. For many aquatic animals, sleep must be light enough to detect threats, the sudden shadow of a predator, the change in water pressure, or the shift in current direction. Yet it must also be deep enough to allow for physical and neurological recovery. In some cases, animals will choose safety over depth of rest, taking many short, shallow bouts of relaxation instead of long, uninterrupted periods. From the outside, the sight of an underwater sleeper can be strangely peaceful. A turtle nestled in coral like a stone statue, a school of fish suspended in the dim light of a reef, a salamander resting beneath a curtain of mossy water plants. It is a reminder that even in a world where danger moves with the tide, the need to rest is universal. Whether with eyes open, half closed, or hidden entirely, life beneath the water finds its own rhythms of stillness in the constant motion of the aquatic world. In warm, sunlit shallows where mangroves breathe and sand settles like dust in a quiet room, upside-down jellyfish lie like living flowers on the seafloor. These are Cassiopeia, pale bells pressed to the substrate, feathery arms lifted to the light. Inside those arms live tiny symbiotic algae that trade sugars for shelter, and to keep the partnership thriving, the jellyfish pulse gently, stirring water through the forest of fronds as daylight feeds the algae. When night drifts over the lagoon, the rhythm changes. The pulsing slows, the body settles. A hush falls over the nerve net. To an untrained eye, it looks like nothing much. To a biologist, it looks a lot like sleep. Calling anything with no eyelids and no brain a sleeper seems bold until you watch what happens across the night. Cassiopeia enters a quiescent state. Movement drops, posture slackens, and responsiveness to the world decreases. Give a daytime jellyfish a mild nudge of water, and it responds quickly, ramping up its pulsing and posture within moments. Try the same at night, and the animal reacts more slowly, as if the threshold for noticing the world has risen. Crucially, this state is reversible in seconds. Shine a light, shift the current, or gently jostle the animal and the pulsing returns. Low activity, higher arousal threshold, and rapid reversibility. These are the hallmarks biologists use to recognize sleep across the animal kingdom. There is a fourth sign that clinches the case. Homeostatic control, the body's tendency to repay sleep debt. If you keep Cassiopeia from settling, by delivering mild pulses of water through the night or periodically disturbing its resting posture, the following day brings a rebound. Pulse rates drop lower than usual, and quiescent bouts lengthen, as if the jellyfish is making up for lost rest. That compensation looks remarkably like what mammals, birds, and even insects do after a missed night. The effect is not simple exhaustion of muscles. The coordination returns on cue when the animal's aroused, and the extra stillness appears only when the disturbance has passed. In other words, there is a regulated need being tracked and repaid. All of this is happening without a central brain. Cassiopeia carries its control system in a diffuse nerve net woven through the bell, with clusters of sensory structures called rhopalia arranged around the rim. Each rhopalium can act like a pacemaker, launching the electrical wave that triggers a bell contraction, and together they keep time for the body's gentle pulse. Instead of a single command center, there are many local conductors, passing cues around a ring and across the net. Sleep, here, is not a master switch thrown in a cortex. It is a collective decision arriving from many small places that, in concert, lower the volume of activity until the world demands otherwise. Why would a creature this simple need anything like sleep? One answer lies in the economy of energy. When daylight fades, the algae inside Cassiopeia stop photosynthesizing. Without that sugar income, pulsing to stir water brings fewer returns. Stillness conserves energy during unproductive hours, and the animal can afford to raise its arousal threshold, because visual predators are less active in the dark, and wave-borne cues travel differently at night in shallow water. Another answer points at maintenance. Even a nerve net needs downtime. Neurons burn fuel and accumulate molecular clutter. Membranes and ion pumps work tirelessly to keep signals flowing. Quiescence is a chance to reset ionic gradients, recycle neurotransmitter packages, and clear metabolites before activity ramps up again with the morning light. There may also be a kind of miniature tune-up happening in the pacemaker circuits. In more complex animals, sleep is associated with synaptic recalibration, trimming and strengthening connections so that signals are efficient the next day. In a rhopalial network, that principle could play out as small adjustments in the timing and coupling of pacemakers. The next morning's pulsing might be more regular, less energetically costly, because the net spent the night quietly rebalancing itself. None of this requires a dreaming mind. It requires only cells that benefit from periodic, coordinated rest. Evidence from other simple animals strengthens the idea that sleep predates brains as we know them. Tiny freshwater relatives, which also lack centralized brains, show cycles of quiescence with the same trio of features: reduced activity, higher arousal threshold, and homeostatic rebound. Move upward on the tree of life and the signature persists. Insects do it. Fish do it. Reptiles show their own versions. By the time we reach mammals and birds, sleep is diversified into stages with wildly different brain-wide patterns, but the core logic is recognizable. Periods of lowered responsiveness, quickly reversible, regulated by need. The lagoon at night is not wholly safe, of course, and Cassiopeia's rest is never absolute. The quiescent state keeps a thread to the outside world. A passing crab, a sudden shadow, a swirl of silt tugged by a new current. Any of these can tip the balance back to active pulsing in moments. The jellyfish is not locked away, it is idling with one hand on the throttle. That blend of lowered activity and rapid response is exactly what you would design if you wanted a system to save energy without losing the option to react. Because the algae in Cassiopeia's tissues depend on light, dawn brings an immediate reason to wake. As the first rays slide through the water, the jellyfish resumes its daytime routine, pulsing to move fluid past the fronds and carry fresh carbon dioxide to the symbionts. Here, ecological context and cellular housekeeping align. The animal sleeps when the factory is closed and works when the lights are on. The elegance of that schedule underscores an important point. Sleep is not just a neurological curiosity. It is a whole organism strategy for matching internal needs to the rhythms of the environment. Thinking of sleep this way reframes our own experience. We often equate sleep with dreams and narrative, the inner theatre of rapid eye movement. Cassiopeia reminds us that sleep can be stripped to its essentials and still matter. At its core, sleep is a carefully regulated drop in activity, a raised threshold for responding, a reversible pause that allows the body systems to catch up and reset. Dreams are a later flourish. The foundation is older and simpler, and it works even when the only decision-makers are a handful of pacemakers humming around a jellyfish's rim. The implications for evolution are profound. If sleep-like states appear in animals without a brain, then sleep did not arise to serve a cortex, a hippocampus, or any of the structures we usually invoke when we talk about memories and emotions. It likely emerged because cells, especially excitable cells, benefit from coordinated downtime. That need would have existed as soon as networks of neurons evolved, and perhaps even before. From that starting point, evolution could experiment, layering on circadian clocks tuned to light, spinning up hormonal regulators, carving sleep into stages, and eventually folding in the strange phenomena we call dreams. There is a gentle humility in recognizing that one of our most intimate experiences has roots in a creature that looks more like a drifting flower than a mind. A jellyfish, bell pressed to sand, arms lifted to starlight that its algae cannot use, settles into quiescence and waits. The lagoon moves around it, faint waves, the whisper of nocturnal fish, the slow outbreath of mangrove roots, and the nerve net keeps its quiet watch. At dawn, the pulse returns. The little forests of fronds lift and stir, and the day's work begins again. Sleep, it turns out, is older than thought, earlier than brains, a patient rhythm that life discovered long ago and never let go. Insects doze in ways that are easy to miss unless you know what to look for. There is no yawning, no pillow, and usually no closing of the eyes at all. Yet their bodies slip into recognizable postures, their senses dial down, and their tiny brains enter a gentle hush. Watch a honeybee in a quiet corner of the hive late at night. The body loosens, the legs sag just a little. Most telling of all, the antennae, those busy feelers that normally sweep and tap, droop and grow still. That droop is one of the neat visual clues of bee sleep. The arousal threshold rises as well. It takes firmer touch, stronger vibrations, or brighter light to bring a resting bee back to alertness. If you keep a bee from resting, it shows a rebound the next chance it gets, spending longer in that still antenna down state, as if repaying a debt. The honeybee colony never truly shuts down, but different castes rest at different times. Young nurse bees that tend brood work round the clock and sleep in scattered short bouts, often right near the brood where warmth and noise are constant. Older foragers consolidate their rest mostly at night, sleeping in the darker, cooler margins of the hive. Drones nap in generous stretches and, like tired teenagers, can be sluggish to get going. Out in the wider bee world, male solitary bees sometimes clamp their jaws onto a stem and sleep outdoors, legs tucked, each one hanging like a tiny ornament in the dusk. Bumblebees may doze wedged among petals after a late feeding, dusted with pollen like someone who fell asleep mid-snack. Sleep matters to bees because their lives depend on memory and timing. A forager's day is a choreography of landmarks, colours, scents, and a moving sun. They read the sky's polarised light, stitch together routes across fields, and then return home to perform the waggle dance, a vibrational map that tells nestmates where to go. When researchers gently restricted bee sleep, the next day's dances grew messy. Angles were less precise, durations wandered, and the information conveyed to nestmates was poorer. After a full, undisturbed night, the dances sharpened again. Sleep appears to steady the inner compass and tidy the map, turning a day's experience into a reliable guide for the colony. That tidying likely happens in brain structures called the mushroom bodies, paired knots of neural tissue involved in learning, attention, and navigation across many insects. In bees, the mushroom bodies integrate odours, colours, and spatial cues. In ants and flies, they are central to many kinds of learning. During rest, synaptic connections in these centres seem to rebalance, a theme that echoes from mammals to fruit flies. Wakefulness strengthens a lot of connections and sleep prunes and refines them, leaving the network leaner, quieter, and more efficient for the next day's work. A great deal of what we know about insect sleep comes from a tiny champion of laboratory science, the fruit fly. In the lab, researchers track a fly's rest with elegant simplicity. A single fly walks in a narrow glass tube. An invisible beam of infrared light crosses the tube. Every time the fly breaks the beam, a device records a tick of activity. When the beam stays unbroken for about 5 minutes, and the fly shows the telltale higher arousal threshold and post-deprivation rebound, scientists score that time as sleep. It sounds basic, but paired with genetic tools that can switch specific neurons on or off, it has revealed a rich sleep machinery. Fruit fly sleep is not random idling. It has structure. There are daytime siestas more common in warm conditions, and longer, deeper night bouts when the clock says it is time to rest. Deprive a fly of sleep by nudging it awake, and it will repay the debt with longer, more consolidated rest the next chance it gets. Certain genes carry heavy influence. Mutations in ion channels and in proteins literally name for their effects. Think of sleepless and insomniac, cut rest dramatically. Others push it higher. Dopamine circuits act as powerful arousal levers. Mushroom body neurons act as a hub where experience, motivation, and the need for rest meet. Memory in fruit flies also leans on sleep. Train a fly on an odour, pairing it with a gentle negative cue, and then allow a good rest, and the next day the association holds far better than if the fly was kept awake after training. Courtship learning shows similar dependence. Males adjust their efforts after experience, and sleep helps lock in that adjustment. Even a kind of spatial learning, remembering a safe, cooler spot in a warm arena, improves with rest. The pattern is familiar. Wake to gather, sleep to settle. These are small brains by our standards, but they obey the same principle that seems to span the animal kingdom. If sleep helps individual insects, does anything like coordination show up at the group level in social species? In a honeybee colony, you will not see the whole hive go quiet at once. Survival demands that some fraction of the workforce is always ready. Yet there is order in the seeming chaos. Foragers tend to rest at night, which lightens the load on traffic near the entrance after dark. Nurses break their rest into shorter, irregular bouts, so that brood care never lapses. In ants, rest is extremely fragmented. Many species take a great number of tiny naps spread across day and night, and because the colony's workforce is huge, those naps overlap without leaving the nest unguarded or unfed. The result is not a choir breathing in unison, but a rolling pattern of staggered quiet, a social mosaic in which individuals take turns dropping into stillness while the superorganism hums on. Ants are masters of micro-rest. Workers pause for seconds at a time in sheltered spots, or even while clutching a brood item, the jaw grip doing the holding while the nervous system idles briefly. Queens in some species take longer, fewer rests, a pattern that makes sense given their singular job and the protection provided by the workers. Whether these bouts count as sleep depends on the criteria you emphasize, but the signatures recur. Lower responsiveness, a characteristic relaxed posture, and a rebound when rest is curtailed. Termites, wasps, cockroaches, and crickets all show their own flavors of quiescence shaped by light, temperature, and colony demands. Navigation shows up again and again as a behavior that gains from rest. Desert ants that run straight out to forage and then home by path integration rely on a neural odometer, an internal record of turns and steps that drifts if sensory processing is noisy. Honeybees calibrate a sun compass that slides across the sky over the day. Night rest stabilizes these computations. After normal sleep, outbound paths are crisper and the return trips more direct. After disrupted rest, routes lengthen and homing gets sloppier. It is not that the insects forget. Rather, the filters that keep small errors from accumulating seem to work better after downtime. Circadian clocks set the schedule on which all this plays. Insects do not depend on melatonin the way many vertebrates do, but they keep time with molecular gears that tick in most cells. Light picked up by dedicated photoreceptors resets the clock each morning. Signals from a tiny group of master pacemaker neurons act like a conductor, keeping tissues in step. When the clock is broken, by genetic tweaks or by constant light, both activity patterns and sleep fragments, temperature nudges the clock too, which is why warm afternoons bring a fly's siesta and cooler nights help consolidate rest across so many species. There is a tempting picture here of sleep as a luxury that busy insects can barely afford. The evidence points the other way. Bees that cannot rest well dance worse and recruit less effectively, costing the colony calories. Flies kept from sleeping learn more slowly and forget more quickly. Ant colonies that are harassed into continuous motion spend more time correcting errors and repairing damage. Small brains do not make sleep optional. If anything, their frugal circuitry may be especially sensitive to the benefits of periodic quiet. Even the outward details of posture tell a functional story. The bee's antenna droop reduces needless sampling of the air, lowering sensory noise while leaving the system ready to snap back. The relaxed leg joints minimize energy use and help the bee stay put. Bumblebees tucking against brood-cut heat loss. Solitary bees clamped to stems avoid sinking chill into their thorax by hanging rather than perching. Ant micro-rests happen in protected corners or under the cover of nest mates that keep watch. Each species wraps sleep in small design choices that make it safer and cheaper. Look closely at a late summer evening, and you may find a spray of wildflowers dotted with dozing bees, each one hooked to a stem by its jaws, dew collecting on the hairs like tiny stars. Inside a hive, in a ring of comb that the sun never reaches, foragers lie like commas between busy sentences, their antennae a little slack, their bodies barely stirring. In a laboratory tube, a fruit fly stands motionless just long enough for the beam to stay unbroken, and molecules inside a handful of neurons begin their quiet work of resetting thresholds and synapses. None of this looks dramatic, yet these are the small stillnesses that make tomorrow's flight straight, tomorrow's dances true, and tomorrow's memories worth keeping. If sleep has a single job in insects, it is to trade a little time for a lot of clarity. A bee that slept dances straighter. A fly that slept learns faster. An ant that slept makes fewer wrong turns in a maze of tunnels and pheromones. Multiply that across thousands of workers, across an entire season, and the gains are not small at all. In the compact world of 6 legs and compound eyes, rest is not an indulgence. It is how a tiny brain stays sharp enough to run a big life. Across the animal world, sleep is not a single behaviour, but a negotiation with danger. Every dozing creature must strike a balance between the need to restore body and brain and the risk of being caught unaware. Along a gradient from safety to peril, sleep changes shape. In sheltered dens and hidden roosts, it can be deep and luxurious. Out on open plains or exposed branches, it is light, fragmented, and always half ready to become wakefulness. Predator and prey do not simply differ in how much they sleep. They differ in where, how, and how deeply they dare to let go. Where the environment is forgiving, deep sleep flourishes. Big cats in secure territories, bellies full after a hunt, can stretch out for many hours of slumber. Lions in particular are notorious for long daily totals, sinking into cycles that include generous helpings of slow-wave sleep and dream-rich rapid eye movement. Bats roosting in caves are likewise buffered from threats and weather. They hang by their tendon-locking feet in dark, stable microclimates where few predators can follow, and the result is consolidated, energy-efficient rest. Small mammals that retreat underground, rodents in burrows, meerkats in fortified dens, benefit from the same architectural safety, which allows deeper stages with higher arousal thresholds and fewer awakenings. Even physiology seems to relax when the sleeping place is secure. Animals in safe refuges show longer bouts of uninterrupted slow-wave sleep, higher proportions of rapid eye movement, and more regular breathing and heart rhythms. Sea lions hauled out on predator-free rookeries can sprawl into steady naps, with both hemispheres of the brain resting together. Owls tucked into cavities rather than exposed branches stay warmer and stiller, and their sleep is measurably less fragmented. Shelter does not merely hide a sleeper, it reshapes the architecture of sleep toward depth, continuity, and repair. By contrast, prey that bed down in exposed places sleep lightly and in short bouts. Deer and antelope lie with legs tucked and heads up, ears swiveling like radar dishes. Horses nap standing, locking their limbs and drifting only briefly before a startle resets their posture. Zebras and wildebeest take their rest in scattered intervals, often after feeding, when rumination continues and vigilance is shared by many eyes. Giraffes, towering over the grass but plainly visible, take the strategy to an extreme. Total sleep time may be as little as a handful of minutes spread across a day, with rare, brief episodes of deeper rest in a folded posture that looks impossibly compact for such a long-necked animal. What they sacrifice in depth, they gain in readiness. Birds show the same gradient. Ducks roosting at the edges of a flock often sleep with one eye open, the outward-facing hemisphere of the brain awake while the inward side rests. Terns on a sandbar or shorebirds on a windy spit arrange themselves so that sentry positions alternate, the periphery taking lighter, more fragmented sleep, and the interior indulging in fuller bouts. Small songbirds in exposed shrubs tuck their heads under a wing for warmth, but they wake frequently, especially when wind rattles branches or moonlight brightens the night. When cover is available, dense reeds, tree cavities, cliff ledges, sleep becomes longer and less punctuated by arousal. Safety alters not just behaviour but sleep's microstructure. In risky settings, slow-wave sleep becomes shallower, the threshold for waking drops, and episodes of rapid eye movement shrink or disappear. The brain's arousal systems remain primed. A twig snap or shift of air pressure pulls the sleeper up through the stages with startling speed. Heart rate and breathing retain more variability, the autonomic nervous system keeping a hand on the brake. In safe places, those same systems stand down. Slow waves grow in amplitude, rapid eye movement expands, and internal housekeeping, from immune activity to memory processing, runs with fewer interruptions. Seasonal demands can flip a species' usual balance. During breeding, many animals lighten and trim sleep to defend territory, attract mates, or care for young. Male pectoral sandpipers in Arctic daylight court nearly round the clock, and have been observed sleeping very little across the brief window when mates are won. Remarkably, those that stayed most active still achieved high reproductive success. Incubating birds reduce rapid eye movement and accept highly fragmented bouts while keeping eggs warm and safe. Colonial seabirds guarding chicks on crowded ledges tuck in for micro-rest between feedings, waking at the smallest touch. The trade-off is stark but temporary. Survival of offspring over perfect restoration for the parent. Mammalian parents pay similar costs. Mother dolphins and their calves spend the first weeks in almost continuous motion, each taking only partial, alternating rest while swimming together. Fur seal mothers at sea use unihemispheric sleep to maintain course, while nursing schedules and foraging demands compress total rest. Ground-nesting hoofed mammals, from gazelles to deer, take lighter sleep during the fawning period and choose bedding sites with wider views, trading depth for early detection. In every case, sleep depth is a dial the animal turns in response to the vulnerability of young, the intensity of competition, and the cost of a mistake. Group living changes the calculus again through shared vigilance. Herds and flocks reduce individual risk because the first to notice danger can rouse the rest. Zebras arrange themselves so that at least some individuals face each compass point. Those at the edges show more frequent headlifts and shorter sleep episodes, while the centre can afford deeper bouts. Meerkat groups rotate roles, with some members taking sentinel positions as the rest doze in the safety of a burrow entrance. Geese and ducks on a shoreline portion themselves so the outer ring sleeps one-eyed, and the inner circle closes both. Fish schooling at dusk drift in coordinated formations, each body shielded by neighbours, and arousals ripple through the group like a wave when a predator passes. Shared watchfulness does not eliminate risk, but it spreads the burden. Even primates reveal how place and company set the terms of sleep. Baboons resting on familiar cliff ledges or sturdy trees show relatively consolidated bouts. Move them to a new sleeping site and their night fragments. Total minutes drop, and awakenings climb sharply until the location becomes familiar. Monkeys that choose higher, thinner branches may sleep lighter than those with access to dense crowns or vine tangles. Social bonds matter too. Individuals flanked by trusted partners rest longer and wake less often than those on the margins of a troop. Safety is a feeling as well as a fact, and brains sleep deeper when bodies believe they are protected. Predators are not always carefree sleepers, and prey are not always anxious. A hungry lion on a contested boundary naps fitfully. A snowshoe hare beneath deep snow can sink into steadier rest than a deer in an open field. Habitat makes predators vulnerable too. Coastal wolf near human activity may sleep lightly and at odd hours. A fox in a snug den enjoys a richer stretch. These exceptions prove the larger pattern. It is the geometry of risk, what can reach you, how quickly, from how many directions, that shapes sleep depth more than a simple label of hunter or hunted. Under all these variations, the purpose of sleep remains constant. Brains need slow waves for synaptic recalibration and cleaning. Bodies need the hormonal, immune, and repair work that runs best when movement and responsiveness are dialed down. When danger looms, animals trim and fragment sleep rather than abandon it. They take many small sips instead of long draughts, pare a rapid eye movement to the minimum, keep one ear open and one eye half lit. When conditions allow, they repay the debt, lengthening bouts and deepening stages until health and performance are restored. What emerges is a picture of sleep as a flexible tool tuned to ecology. In sheltered spaces and trusted company, animals sink into depth, letting the night do its quiet work. In exposed places, they hover near wakefulness, stacking brief rests into a workable whole, while the world turns watchful around them. Predator and prey differ not in need, but in strategy. One can afford to dream longer, the other learns to dream lightly. Both are playing the same game, maintaining a mind and body sharp enough for tomorrow, with rules written by the landscape, the season, and the eyes that might be watching in the dark. Night can be deafening. The air shivers with cricket strings, ponds throb with frog choirs, and nocturnal mammals rustle, squeak, and chatter their way through the dark. Yet all of these noisy creatures still need to sleep. The trick is not silence, it is predictability. Brains, large and small, are good at turning a steady soundtrack into background, letting familiar patterns fade while keeping a sentinel circuit tuned for odd, unexpected notes. Where we might reach for earplugs, wild animals reach for evolved filters that separate the hum of ordinary life from the sharp edges of danger. Crickets are a study in musical multitasking. A male chirps by rubbing a scraper on one wing across a toothed file on the other, creating pulses at a carrier frequency tuned to carry through night air. He will sing, and pause, repeating a rhythm that to other crickets is both advertisement and metronome. When the chorus swells, each individual is surrounded by sound, yet crickets still take their brief quiescent bouts. Part of the solution is neural tuning. Their ears and auditory interneurons are most sensitive to conspecific frequencies and temporal patterns, while abrupt ultrasounds, the signature of a hunting bat, pierce the filter and trigger instant action. The noisy, regular chorus becomes a kind of acoustic wallpaper. The sudden, high-pitched click of danger is what matters. Frogs perform the same alchemy at a wetter venue. A breeding pond can explode with overlapping calls, croaks, trills, peeps, and booms, each species occupying its own slice of acoustic space. Males call, females listen, predators listen too. Between calling bouts, and especially by day when calling a baits, frogs rest in vegetation, under banks, or pressed into mud. Their inner ears are split into two sensitive ranges, one tuned for low notes, one for higher, and brainstem circuits can damp responses to the frog's own call while preserving sensitivity to the frequencies that spell predator. Repetition helps. A chorus that rolls on for hours becomes the pond's heartbeat, and the sleeping frog's threshold for arousal rises to match it. A twig snap, a new rhythm, or a rush in the water, and the dial flips back to alert. Nocturnal mammals add another layer of noise. Footsteps through leaf litter, sniffs and squeaks, territorial calls, even the fast staccato of bat echolocation. Many roost or den in places that are noisy by design. Cave colonies of bats, attic lofts full of mice, tree hollows humming with social chatter. They sleep anyway, thanks to a mixture of mechanics and software. In bats, tiny middle ear muscles contract during self-generated calls, briefly dampening the eardrum so the animal does not deafen itself. Auditory pathways also reduce their gain at the instant of vocalization, then rebound to catch the returning echoes. In rodents, predictable nest sounds are quickly habituated. Novelty detection circuits flag only the oddball notes. A constant murmur means everyone is here and nothing unusual is happening. Silence, paradoxically, can be alarming. Sleeping through noise is easier if you can shape your soundscape. Many animals choose sleeping sites with acoustics that favour safety. A burrow muffles distant thunder and wind while amplifying nearby scrapes that matter. A tree cavity softens the chorus but lets through the vibration of a climbing predator. A reed bed hushes far-off calls while translating footsteps into rustles. Birds tuck their heads under a wing not only for warmth, but to muffle sound at one ear and reduce startle from every small noise. Seabirds on ledges, penguins in rookeries, and gulls on open beaches settle, where surf provides broadband noise that masks faint disturbances, yet still allows the slap of a nearer wave, or the footfall of a predator to stand out. Brains help by changing how sound is handled during sleep. Across vertebrates, sensory gating increases in deeper stages. The thalamus passes fewer signals upstream, and cortex responds less to repetition, while remaining suspicious of change. Light, fragmented sleep in exposed sites keeps the gate half open. Deeper slow-wave bouts in safer refuges let predictable noise glide past with barely a ripple. There is clever specialization too. Frogs' efferent auditory fibers can modulate hair cell sensitivity. Bats coordinate ear dampening with each call. Even insects reduce responsiveness to their own rhythms after prolonged exposure. The theme is consistent. Reduce energy spent reacting to what is ordinary. Preserve the reflex for the rare. Do all this, and you unlock the strangest benefit of a noisy night. Sound can become a safety signal. A colony's steady murmur tells every individual that bodies are present, sentinels are awake, and no alarm call is pealing. Cricket's overlapping songs imply no bat has swooped, because a hawk among the reeds or a bat among the hedges would thin the chorus in a heartbeat. In roosting bats, a low level of social chatter persists even as many individuals sleep, and it functions like a living lullaby. Group cohesion confirmed, nothing acute unfolding. Geese, ducks, and many shorebirds produce soft contact calls as they settle. When those calls stop abruptly, heads lift. When they continue, the centre of the flock dares a deeper doze. The timing of noise also matters. Many callers do not sing continuously. They run on duty cycles. A male cricket or tree frog belts out a burst, rests, then belts again. During the rest window, arousal thresholds can climb, letting microbouts of quiescence stitch together into meaningful recovery. In a dense chorus, the animal experiences a kind of acoustic averaging. While neighbours carry the song, any one individual can lower its gain. Hummingbirds do a similar trick with the visual world at night by entering torpor. In the acoustic world, chorusing species use their neighbours as both amplifier and guard, freeing brief slices of time to let the nervous system idle. Not all environmental noise is helpful. Wind gusts saturate the ears with broadband hiss. Heavy rain drums through the night. Insects, birds, and frogs can be drowned in their own festival. The common coping strategy is selectivity. Sensory neurons adapt to constant amplitude noise. Midbrain circuits emphasize onsets and changes. Motor systems stabilize posture to reduce self-generated rustle. Where possible, animals choose leeward hollows, the downstream side of shrubs, or the quiet back of a log where wind is less chaotic and rain on leaf hits at a softer angle. Herds arrange themselves so bodies block the worst of the gusts. Bat clusters press tight, turning many flapping cloaks into a single dull roar that is easier to ignore than 100 separate flutters. There is nuance in how noise and safety interplay across seasons and life stages. During breeding, the urge to call can override the urge to sleep, and many males pay a short-term cost in rest to shout their best songs. They compensate by sleeping longer or deeper once the chorus quiets, or by shifting to safer, more insulated sleeping sites by day. Parents with young shift the balance the other way. They lighten sleep and stay alert to the tiniest squeak, and the colony's background noise becomes a pulse they check continuously for any hint of alarm. In some cases, families or subgroups develop distinctive contact notes that cut through the clatter, allowing selective waking for the sounds that matter most. For humans, noise is often a villain. For wild animals, it is information, a stream of probabilities about who is near, which predators are active, and whether the present moment demands attention. In that calculus, steady chorus can be a green light. A croaking pond says, "Heron not here." A cricket meadow says, "Bat not diving." A bat roost's purr says, "Hawks not circling." The animals that live in these places have nervous systems that exploit those statistical hints, sinking a little deeper when the soundtrack is right and skimming near wakefulness when it is not. All of which makes the nocturnal soundscape feel different once you learn to hear it. The cricket's pulse is not just romance, it is also cover. The frog's choir is not only competition, it is also community noise that lets neighbours rest on rotation. The rustle of mice in straw is not mere disorder. It is a living barometer whose steadiness lets a mother doze while pups twitch. The noisy night is not the enemy of sleep. It is the backdrop that, when familiar and continuous, tells 1,000 small sleepers that the world is ordinary and that they can, for a little while, safely drift. Sleep can be a solitary luxury, but for many animals it is a team sport. When the night air turns sharp or the daytime sun is unforgiving, Bodies press together and turn a crowd into a blanket. In burrows, caves, crevices, and wind-scoured ice fields, social sleepers solve two problems at once. They slow the drip of heat from their bodies, and they share the burden of vigilance so no one mind has to stand guard forever. The trick is to take all the benefits of a cuddle pile and avoid its costs, because warmth moves easily through fur and feathers, and so do parasites and pathogens. Meerkats are small bodies in a big desert, and their solution is architecture plus friendship. As dusk draws a line across the Kalahari, groups stream into underground dens that can include several chambers connected by sinuous tunnels. Down there the air is still, the temperature steadier, and the sand walls store the day's heat. Meerkats heap into a mound of stripes and tails, pups wedged safely into the centre. Social thermoregulation does the physics. By reducing the surface area exposed to the air, the pile loses less heat per animal, and the inner core stays warmer than any one meerkat could manage alone. With warmth comes rest. They sleep deeper and wake less often than a lone animal curled at the edge of the world. That same closeness lets them divide the labour of safety. Even in the dark of a den, a rustle or a scent can stir the outermost sleepers first, and a chain of small arousals ripples across the group while the interior continues to doze. Above ground, they extend this social choreography into daylight with sentinel duty. Individuals take turns standing tall, while the others forage or nap, rotating the cost of vigilance through the group so no single animal pays it all. They even manage the disease risk that comes with crowding. Colonies shift sleeping sites, abandoning old burrows and digging new ones, a habit that helps shed fleas and reduce the build-up of pathogens in a single nest. Grooming reinforces the truce. Paws and teeth comb through fur, picking off hitchhikers and reinforcing bonds that make sharing heat feel safe. If meerkats are sand engineers, emperor penguins are wind engineers. Through the long Antarctic night, fathers incubate eggs on their feet while mothers are far at sea. The temperature outside can fall to levels that would steal the breath from most living things. The answer is the famous huddle, a slow-moving cathedral of feathers made from many hundreds of birds. Each penguin leans inward just enough to share warmth without crushing the egg tucked under a feathered belly. Air trapped in dense plumage and between bodies becomes an insulating layer, and the interior of the huddle warms dramatically compared to the air beyond the wall of backs. Then the entire mass begins to creep in tiny steps, like a living conveyor belt. Birds on the frigid edge inch their way toward the comfort of the centre. Birds at the centre yield their place and rotate outward. No one stays exposed for long. The movement is so orderly that waves of shifting positions can be seen rippling across the colony, a choreography the birds achieve with local cues rather than any central command. Penguin physiology leans into the strategy. Tight vascular control keeps blood flow low in exposed feet and flippers, while countercurrent heat exchangers in the legs and wings recapture warmth before blood returns to the core. Sleep within the huddle comes in many short episodes, layered between postural adjustments and the slow shuffle. It is not luxurious, but it is enough. The noise of neighbours and the press of bodies become the background hum of safety. When a gust slices through the ranks, heads lift as one. When it passes, eyelids droop in 100 directions and rest resumes. Disease still matters. Any crowd is a marketplace for microbes, but the Antarctic cold prunes many pathogens at the door, and the payoff in heat and chick survival is enormous. Bats bring the problem indoors. Many species form maternity colonies in caves, mines, belfries, and hollow trees, clustering by the dozens or the thousands. Hanging close together does for bats what huddling does for penguins. It lowers each mother's energetic cost of staying warm and keeping milk flowing for a growing pup. The physics is the same, but the challenges are different. Caves are stable but damp. The air is still, but microbes and ectoparasites can find a foothold. Bats counter with behaviour. Colonies split and fuse, switching roosts through the season so that parasites and fungi do not get endless access to the same bodies. Allogrooming picks off mites and bat bugs. Some species show a striking ability to synchronize arousals from torpor. When one cluster warms, neighbors often follow, creating pulses of movement that may disrupt parasites and reset the microclimate. Group warmth is not a free lunch. Pack bodies together and heat loss drops, but the probability of passing on a pathogen rises. Animals manage this trade-off with spacing rules, timing and membership. In penguin criege, chicks huddle most tightly in storms and relax their spacing on milder days. Meerkats keep their dens clean by using latrines outside and by rotating sleeping chambers. Bat colonies shift roosts and sometimes segregate by reproductive status, which can limit the circle of close contact. In many species, the sick draw back from the centre of social life, a behavioural immune response that protects kin by reducing contact during the period when a disease is most transmissible. Even simple acts like choosing the driest chamber of a cave, the breeziest side of a burrow, or a roost with a bit more airflow can push the microscopic odds toward health while preserving most of the thermal gain. Beyond warmth and microbes lies time itself. Groups that sleep together tend to keep time together. Social cues become clocks. The first few penguins to stir at the colony edge nudge neighbours into wakefulness, and the wave spreads across the ice. In a meerkat group, dawn begins with a chain of yawns and stretches near the den entrance. The chorus of low chatter escalates, and bodies emerge in a predictable order. Within minutes, they're facing the sun, soaking heat into fur like portable solar panels, before moving as one to forage. In bat roosts, emergence at dusk is a spectacle of synchronization. A few scouts swirl into the evening, then the stream thickens as the colony's consensus time arrives. This alignment brings benefits. It reduces the odds that a lone individual faces a predator and concentrates foraging when conditions are best. Synchronized rest also appears at shorter scales. In flocking birds on a shoreline, one half of the flock may doze while the other half preens or feeds. After a short interval, the roles reverse. In herds of ungulates, head lifts and ear flicks propagate like slow-motion alarms. When nothing follows, many heads lower again in unison. This ebb and flow lets individuals dip deeper into sleep for brief windows, confident that neighbours will tug them back to alertness if something changes. The result is not uniform slumber, but a rolling quilt of micro-sleeps that, stitched together, meet the brain's nightly quotas. If social sleep brings such strong advantages, why not cuddle all the time? Heat can overshoot. Pack too tight in mild weather and bodies risk overheating, which is as disruptive to sleep as the cold. Many huddling species therefore build in vents and release valves. Penguin groups open small gaps that let steam bleed away. Meerkats in a warm season sprawl rather than heap, touching at shoulders and hips but leaving air between bellies to shed heat. Bats alter roost choice with the calendar, seeking cooler hollows in midsummer and tighter cavities when nights turn cold. The goal is not maximal closeness, it is optimal closeness, tuned to wind, moisture and the invisible arithmetic of energy. There is also the matter of who gets the best seat in the huddle. Physics says the middle is gold. Behaviour makes it fair. Penguins rotate by inches. Meerkats let pups and high-ranking females take inner spots. Bats' pups cling to their mothers' bellies, effectively riding inside the warmest zone wherever the mother lands. In many species, these rules are enforced by gentle shoves rather than fights. The point is not dominance, but throughput. If everyone keeps moving, everyone survives. Even sound and smell help hold the system together. Contact calls ping through a penguin huddle and reassure neighbours that the group is intact. A rumble of purrs and squeaks vibrates through a bat cluster. If that purr goes thin, more heads lift. Meerkat scent marks on tunnel walls create a familiar perfume that lowers stress and may help synchronise physiology. Heart rates settle faster, and the whole pile sleeps more deeply when the den smells like home. These sensory threads stitch the sleeping mass into a single organism that notices, warms and quiets itself by reflex. What looks like a heap of animals is, on closer inspection, a set of rules played out with feathers, fur and patience. Huddle when it is cold, spread when it is warm, rotate the edge to the centre and the centre to the edge. Share the watch. Keep the nursery in the sweet spot. Change addresses often enough to shake the fleas. Wake together when the first hint of trouble twitches at the margin. No individual has to know the whole plan. The plan emerges from many small choices that are easy to make in the moment, and together those choices buy sleep that is warmer, safer, and more restorative than solitude could ever offer. In a cave, on an ice field, in a burrow under stars, social sleepers prove that rest is not only about closing eyes, it is also about opening space for others, a wing's breadth, a shoulder's lean, a shared breath that turns a harsh night into something survivable. Warmth passes inward, trust passes outward, and in that exchange, the animals of the crowd find a way to do the quiet work of repair, while the world turns cold or wild outside. Parenting can rewrite the body's timetable. In the wild, it often tears up the usual schedule and draws a new one in haste, with sleep squeezed into the margins between feeding, guarding, and keeping small bodies warm. Across cliffs and ice, through surf and savanna grass, parents trade depth of rest for a young life's safety. The result is not just less sleep, but a different kind of sleep, lighter, more vigilant, and stitched together from fragments that would exhaust a non-parent but somehow carry a family through the days and nights that matter most. Seabirds make the bargain in bright wind and salt. During courtship and incubation, many species still find time for generous bouts of rest, dozing on ledges or bobbing at sea. Once a chick cracks its shell, sleep contracts. A parent on the cliff edge rarely closes both eyes for long. Birds can sleep with one hemisphere at a time, and a guarding adult will often keep the eye facing the colony open, while the other side of the brain slips into slow waves. On narrow ledges where a stumble would be fatal, posture stays tense, and the head lifts at the faintest scrape. Kittiwakes and guillemots, terns and skuas all show the same pattern. Between feedings, a watchful calm. During storms or predator flybys, a long wakeful vigil punctuated by seconds-long micro-rests. It does not look like sleep, unless you know how to spot the softening of the neck, the steadying of breath, the brief flutter beneath a closed lid before another scan of the horizon. On the water, the trade-off shifts but does not vanish. Albatross and petrels range so far to find food that a foraging adult must rest on the wing or on the swell, yet during the chick-rearing weeks those rests are shorter and shallower than at other times of year. Nap on the ocean too deeply, and you may miss a wind change or a squall. Delay too long, and the chick on the rock will face a hungry night. Parents repay the debt later, lengthening their sleep once the chick is stronger or fledged. In colonies where skuas patrol and gulls raid, sleeping deeply is a luxury that returns only when little wings are ready for the air. Penguins add cold to the equation. An emperor father on the ice incubates through the long polar night, egg balanced on his feet, a living bridge of warm blood between chick and deathly air. He rests in short, shallow bouts tucked within the huddle, and wakes whenever the column of birds begins its slow, collective shuffle, edging the exposed toward the centre and the centre back toward the weather. Other penguins keep similar hours when chicks are small, sleeping in scattered snatches between brooding and trips to sea, the sound of neighbours serving as both lullaby and early warning. On the savannah, a lioness with cubs proves that even a top predator can sleep like prey. A pride without small cubs can lounge for what seems like half a day, sprawled in golden heaps with tails twitching in dreams. With cubs in a den, that picture changes. For the first weeks, mothers often keep the cubs hidden away from the pride, and from eyes that mean harm. Hyenas, leopards, even incoming male coalitions. Nights become long corridors of listening. A lioness beds down near the den mouth and dozes with one ear in the grass. Every few breaths the head lifts. The wind is tested. The body repositions to place scent down breeze. Sleep arrives in fragments, then breaks for a check of the dark. If danger presses, she will move the cubs one by one to a fresh hollow or a thorny thicket that breaks scent into tatters. Sisters and close kin help carry the load. Lionesses often synchronize births, forming crèches in which cubs nurse from more than one mother and guards rotate. Even then, rest for any one mother is lighter than usual. The periods when pride mates patrol or when hyenas call close by are the periods of least sleep. The eyes close, but not for long. The heart steadies, but not to the deep, slow rhythm of a carefree night. Only when the pride is reunited and the cubs begin to explore in daylight does a mother take something like a proper nap, and even that is a watchful kind of relaxation. A bask with ears alert for the small bark that means a cub has wandered too far. Hunting pushes against sleep from the other side. With milk to make and mouths to fill, lionesses often shift more of their activity into the cool hours, when endurance and stealth go farther. A night of failed hunts can mean a day of near wakefulness. Garden cubs while hunger sharpens. Here sleep becomes transactional. A few minutes as the sun climbs and the cubs nurse. A longer, calmer bout once bellies are full and the shade is deep. If the pride rests in a well-known thicket or on a favoured kopje, the bouts lengthen. If the day heats and scavengers pester, they splinter into smaller pieces. In the sea, motherhood rewrites sleep most dramatically. Dolphin and porpoise calves are born lean and poorly insulated. For weeks, mother and calf swim almost without pause, a duet of motion that keeps the pair warm, coordinated and close to air. The calf rides in echelon beside the mother's flank, slotting into the pressure wave that her body carves through the water. That slipstream cuts the calf's effort. The mother sets the speed. Unihemispheric sleep, letting one half of the brain rest while the other steers, turns from a convenience into a lifeline. The awake hemisphere keeps time with breath and watches for sharks or boats. The resting hemisphere gathers what slow waves it can. Calves show their own version of this, and for a surprising span of days they and their mothers function on what looks, by human standards, like almost no conventional sleep at all. Whales scale the pattern up. A humpback mother guides her calf into quiet coves and coastal shallows, teaching breath rhythm and the etiquette of tides. Rest comes as hovering near the surface or as gentle, parallel glides, the mother placing her body between calf and the open blue while she alternates halves of her brain. Large oceanic dolphins and orcas keep pods tight when young calves are present, and the adults collectively lower their thresholds for sleep so that vigilance is never absent. When calves are older and the blubber thicker, mothers lengthen their resting bouts and let deeper fragments of sleep return. Pinnipeds invent their own compromises. A fur seal mother at sea must forage and still meet a pup on shore for nursing. At sea she may drift dive and catch micro-sleeps in the water column, or use one-sided sleep to keep a heading. On land with a pup she sleeps lightly and in short spells between bouts of nursing and grooming. Elephant seal mothers on crowded beaches rouse at any sharp movement, and often position their bodies to create a barricade against larger males that could crush a pup in a dispute. Sea otter mothers hold pups belly to belly on the surface, sometimes wrapping the pup in kelp to keep it from drifting. They nap but lightly, waking to groom the fur that keeps a pup afloat and warm. How do these parents avoid the worst consequences of so little deep rest? Part of the answer is architecture in the brain. Unihemispheric slow-wave sleep lets marine mammals meet two imperatives at once: breathe and rest. Birds guarding chicks borrow the same trick, keeping one eye open on the world. Part is chemistry. Hormonal shifts during parenting change thresholds and priorities. Prolactin levels rise in birds and mammals with young supporting parental behaviours, and, it seems, altering how tiredness is felt. Oxytocin strengthens the bond that keeps a mother attentive without constant conscious effort. Stress hormones edge upward in proportion to risk, sharpening senses at the cost of depth. None of these is a magic shield, but together they reshape how sleep pressure is managed. There is also efficiency. When sleep is scarce, the minutes that do occur often carry heavier slow waves, as if the brain squeezes more restoration from less time. Parents show strong rebound once the urgent period passes. Seabirds lengthen sleep when chicks have fledged. Lionesses deepen their naps when cubs are old enough to follow the pride. Dolphin mothers return to more typical patterns when calves can keep warm and breathe on schedule without help. The debt is paid back not all at once, but in a season's worth of slightly longer, slightly deeper nights. Risk management turns small choices into bigger safety. Seabirds choose ledges with shelter from prevailing winds, and a clear view of the approach routes favoured by skuas, so that a few seconds of extra warning replace a few minutes of sleep. Lionesses pick dens with complex entrances that baffle scent and sound, so that light sleep can be just light enough. Dolphin mothers favour bays where swell is low and boat traffic small, so that alternating halves of a brain can predict the water's push and pull. Every choice buys a fraction more rest, or a fraction more safety. Added together across days, those fractions are a survival strategy. What looks like sacrifice is also a kind of confidence in the body's flexibility. A seabird parent running on micronaps can still bring back a billful of fish. A lioness blinking away a night of hail-light sleep can still explode into a sprint. A dolphin mother who has not truly stopped moving in many days can still turn, surface, and nudge a calf into its first perfect breath. Sleep bends, thins, and fragments under the weight of care, but it does not break. It waits for the moment a chick grows feathers against the wind, a cub's legs lengthen into gamekeeping speed, a calf's blubber seals in warmth. Then, slowly, the nights thicken again. There is tenderness in the way nature spreads the cost. Colonies and prides and pods are not just social clubs. They are safety nets that let parents borrow minutes from neighbours, swap watch for warmth, trade a turn at the edge for a turn in the middle. The physics of huddles, the choreography of rotations, the quiet rules of who lies where and wakes when. All of it keeps a parent's eyes a little clearer when it matters. In that web, sleep is never simply lost. It is transformed, shared and recovered, because the next hunt, the next storm, the next long swim will ask for strength again, and a parent's body knows how to find it. Under a quiet reef where the moon combs silver lines across the water, an octopus rests in its den, and the skin across its mantle blooms and fades in quick, patchy bursts. A constellation of chestnut freckles, a slick of velvet black, a sudden wash of sand pale. No hunter has arrived, no crab scuttles past. The only thing moving beyond the tide is a story inside the octopus. Cephalopods carry pigments in tiny elastic sacs called chromatophores, each ringed by muscles that expand or shrink the spot in a blink. Beneath them sit mirror-like iridophores that throw back greens and blues, and milky leucophores that scatter whatever light is available. With that toolkit, these animals can write pictures on their skin when awake, and, uncannily, while asleep. Octopuses, cuttlefish, and some squid pass through two sleep-like states. One is quiet, colours muted, breathing slow, eyes hooded. The other is brief and lively. The eyes twitch, the siphon flutters, and the skin plays rapid patterns that look suspiciously like the waking repertoire. Camouflage mottles, high-contrast warning bars, even the wave-like passing cloud used by cuttlefish to stalk prey. The sequence runs for seconds to a minute, then vanishes back into calm and repeats later in the night. Scientists call this active sleep, a label chosen because it resembles the vivid phase of mammalian and avian sleep that so often host dreams. Whether a cephalopod experiences imagery, we do not know, but the behaviour is consistent. Bursts of colour and motion separated by longer, quieter stretches, as if a rehearsal were taking place beneath the skin. Why paint while asleep? One idea is rehearsal in the strict neural sense. In rodents, neurons that fired along a maze replay during sleep. Perhaps motor circuits in cephalopods do something similar, and the skin shows the echoes. A cuttlefish might briefly practice the freeze and flash sequence that pins a shrimp. An octopus might replay the snap from pale sand to dark rock. Another idea is maintenance. Chromatophore muscles and their controlling neurons are fast, precise, and numerous. Coordinated bursts could be a systems check, the biological equivalent of flexing a hand to keep circulation smooth. A third view is that sleeping colour is a reflexive spillover. Activity that sweeps through visual and motor centres during active sleep incidentally recruits the chromatophore network, with no aboutness at all. The safest conclusion is that sleeping colour is a window onto a busy sleeping brain, whether it is rehearsing, resetting, or simply humming. Fish have their own night palette. Many reef species grow paler when at rest, patterns soften, and brilliant daytime hues dim to pastel. Others switch into a dedicated sleep livery that breaks up the outline. Butterfly fish and damselfish often wear a dark eye mask with a paler body by night, a combination that confuses a predator's strike. Parrotfish tuck into crevices and secrete a clear mucus cocoon that may muffle scent and deter parasites. Inside, their colours fade a shade or two. Pelagic fish that cannot hide often dial down saturation and hover in the water column with minimal motion. Because most fish lack eyelids, the easiest way to spot rest is to watch the posture and the palate. A hover close to the bottom or within coral, fins barely correcting, colours dulled, and a slow response unless something truly unusual happens. The chemistry behind these night uniforms is old and economical. In darkness, many animals raise melatonin, a hormone that whispers, "It is night," to tissues across the body. In fish, melatonin can act directly or indirectly on pigment cells called melanophores, encouraging pigments to gather and lighten the skin. Other chromatophores, xanthophores with yellows and erythrophores with reds, respond to internal signals too. The result is a gentle blanching that reduces contrast under starlight, and crucially one that does not require constant neural attention. When a fish must wake, neural signals can override the hormonal drift quickly. If the night stays quiet, the skin holds a low-key palette that blends better with the dim reef. Cephalopods add a twist. Their skin is not just a screen. In a limited way, it is also a sensor. Proteins related to visual pigments sit in the skin, and patches can respond to light. Not enough to form images, but enough to sense brightness and perhaps contrast. In the wild, that may help a resting octopus maintain a suitable background tone if light shifts with a passing cloud or the lensing of waves. Yet the showiest sleep colours often appear in near darkness, deep in dens, or under a moonless sky. That points to an internal driver, a brain clock setting the tempo of quiet and active sleep, with motor circuits briefly grabbing the chromatophore network and running through a remembered routine. Camouflage, dreaming, or reflex? For fish, the night palette looks like camouflage first and physiology second. A pale or mottled rest state is safer and cheaper. Safer because it softens the silhouette for hunting morays and octopus. Cheaper because maintaining high contrast displays costs energy. For cephalopods, the quiet state is likely the camouflage default. The bright bursts during active sleep probably do not hide anything. They may even be risky if a predator peers in. That risk is one reason researchers suspect an internal purpose, a cost paid for whatever active sleep is doing for memory, learning, or neural reset. Just as a human mutters dream talk with no survival benefit, a cuttlefish's sleeping stripes seem unlikely to be serving the night's colour rules. Lighting in the wild writes its own terms. Near the surface, a bright moon can cast sharp shadows. At depth, only blue-green remains, and even that thins quickly. Reefs under a full moon are bright theatres where hunters patrol by sight, and many fish bleach to avoid popping from the background. During a new moon, the sea is inkier and bioluminescence more conspicuous. A sudden movement can light a trail of tiny stars and betray a sleeper, so stillness becomes the first rule and patterning a second. Surge matters too. In wave channels, light strobes with each swell. Fish resting there choose alcoves where the strobe is damped, and cephalopods wedge deep and remain plainly coloured, refusing the flicker's invitation to twitch. Artificial light at night complicates everything. Harbours and resort shorelines wash reefs with steady glow, blurring the natural signals that lift melatonin and cue night colours. Some fish stay vivid longer, delay rest, or rouse more easily. Others adopt a permanent twilight palette that is neither safely drab nor fully alert. Cephalopods hunting under pier lights learn to use the brightness, but those same lights may compress the timing of quiet and active sleep or shift them later. In places where night never truly arrives, the colour of sleep can look like the colour of confusion, a palette pulled between internal clock and lamp. Biology sets limits on what colours can do during rest. Chromatophores are muscles, holding them maximally expanded is work. Many cephalopods settle into a tone that demands little tension. Not pure white, which can be conspicuous, and not pure black, which is costly to sustain, but a comfortable middle with mottling from partially open sacs. The bright bars and eye spots are quick to paint and quick to erase. They are not built to last. Fish pigment cells are slower, designed for minutes and hours rather than seconds, which suits the night shift. A fish's gradual fade to sleep colours and slow return at dawn match the reef's dimmer switch. There are exceptions that clarify the rules. Some gobies sleep buried all the way to their eyes. Colour is irrelevant beneath sand. Cavefish live without day altogether and carry attenuated pigments. Their rest tracks hunger and safety more than light. Cuttlefish on open sand at night sometimes keep a faint ripple of passing cloud, the sliding shadow they use while hunting. It makes little sense as camouflage during rest, which is exactly why it reads like an involuntary replay. Octopuses that have just moved dens often show more frequent active sleep bursts that include the patterns used during the evening's relocation. A hint, not proof, that recent experience primes the night's skin stories. What a human sees at night is not what every hunter sees. Many reef predators are tuned to blue-green. Some detect polarized light, others hunt near-sighted by motion. A fish whose night mask seems obvious to us might look surprisingly subtle to a moray eel's vision. Cephalopods themselves are probably colourblind in the human sense, with a single visual pigment, yet they sense contrast exquisitely and may exploit chromatic aberration to glean colour from focus. Their skin, meanwhile, knows enough optics to match coarse patterns without passing hue as we do. There is a quiet humour in the idea that some of the ocean's brightest show-offs grow understated for bed, while some of its stealthiest hunters sometimes bloom into high-contrast pyjamas when nobody's looking. It is easy to project our nightly habits onto them. Lights down, colours off, dreams on, but the sea edits the script. The palette of rest is tuned to currents, moon, depth, and the kinds of eyes that search the dark. In cephalopods, the palette can briefly become a moving diary of the day's work. In fish, it reads like a letter to the night that says, "Nothing to see here," written in tones that take advantage of the physics of dim water. By dawn, hues slide back toward daytime purpose, melatonin ebbs, pigment cells disperse, masks lift, bars sharpen. A parrotfish cracks its cocoon and flushes turquoise. A butterfly fish trades its night visor for a sunrise stripe. A cuttlefish stirs, gives one last drowsy ripple of pattern, and slips into the exact outfit needed for hunting over rubble. The colours of sleep sink beneath the colours of doing, and the reef's quiet spectrum swells back to daytime brightness. For a few hours each night, though, the water keeps a gentler palette, the pale of staying hidden, the mottled of not quite being a shape, and in one corner here and there, a sudden mural that is a dreaming skin or a reflex unspooling in the dark. Night used to be a place, not just a time. It arrived in a sweep of shadow, and the world's rhythm shifted to the slower metronome that darkness brings. In many towns and cities the night never quite lands. Street lamps, billboards, windows, and stadium beams stitch together a soft, permanent noon that spills far beyond the pavement, creeping over fields, wetlands, and coastlines. For wild animals, that glow is not simply a brighter backdrop. It is information their bodies take seriously. Light says day, and when the message comes at the wrong hour, clocks drift, hormones misfire, and sleep becomes shallow, scattered, or strangely timed. Urban birds are often the first to show the effect. Under constant glow, many species sing earlier in the morning and later into the evening, lengthening the bookends of their day and shrinking the quiet middle where real recovery should happen. Blackbirds nesting along lit streets wake sooner and roost later than their forest cousins. Their internal clocks shift. Melatonin, the hormone that rises in darkness and nudges the body toward rest, stays lower for longer. The result is a life nudge toward permanent jet lag. More time awake does not always mean more time earned, because the hours of high-quality sleep shrink. Even when birds do doze, they rouse more often at the sweep of headlights or the flare of a security lamp, turning what should be deep, slow-wave rest into a mosaic of micronaps. For migrants, light at night is more than a nuisance. It is a lure. Skyscrapers and floodlit arenas pull birds off course. They circle and call, burning fuel they cannot spare. Many push onward through the small hours to make up lost time, arriving at stopovers with a sleep debt they must repay, while also dodging day predators and finding food. That debt does not stay abstract. A tired migrant navigates less precisely, judges distances poorly, and may lose the fine edge of vigilance that keeps a forager alive in unfamiliar ground. Bats thread a narrower corridor. Many species are light-averse, avoiding bright streets and parking lots where moths swirl. Their usual foraging routes become broken ladders of shadow, and the commute between roost and hunting ground lengthens. Some bat species exploit insects drawn to lamps, but the winners and losers are shuffled. Light-tolerant bats thrive. Light-shy species fall back. Inside day roosts, a single bright window or a poorly shielded floodlight can leak into crevices and rafters. When night never feels fully dark, roosting bouts become more restless and more easily interrupted, and mothers nursing young may spend precious calories settling again and again instead of sleeping. Insects carry much of the burden. A moth that should rest under a leaf can spiral for hours around a globe of glass, spending energy it cannot replace and exposing itself to predators that patrol the halo. Nocturnal pollinators shift their circuits toward lit patches, leaving dark flowers unattended and changing which plants set seed. Even when insects do find shelter, artificial glow can blur the boundary that normally presses the nervous system into a low-activity state. Rest becomes fitful. Dawn cues arrive too early. Life histories turn by a few wrong degrees and wander. Amphibians feel the light with their skin as much as their eyes. In many frogs, the glow of a roadside is enough to suppress calling. Courtship shrinks. Nights of booming songs turn to scattered peeps, and the intervals between calls, where a male might catch tiny sips of sleep, collapse into vigilance. Tadpoles in lit ponds swim more at night and rest less, becoming easier targets for fish and dragons that love a silhouette. Salamanders crossing illuminated trails pause more often, misreading safe darkness for risky day, which stretches a simple trip into a gauntlet and cuts the time available for real rest underground. Along coastlines, the night's script is rewritten in amber and white. Beachfront lighting disorients sea turtle hatchlings, sending them toward bars and boardwalks instead of the surf. Adults that would normally crawl ashore on moonless nights may delay nesting or abandon it altogether if the sand never feels dark. Under piers, constant brightness keeps some fish on the move long after they should have faded into their sheltered pallets, shrinking the window for repair and making them more visible to prowling predators whose vision thrives in the same spectrum our LEDs cast. Noise arrives as a partner to lighten the city's long day. Traffic hums, sirens flare, aircraft pulse, fans drone, and human voices rise and fall in a tide that rarely retreats. Animals cope by filtering out the predictable and spiking awake at the odd. That strategy saves energy but can shred sleep when novelty never stops. Roosting birds near highways lift their heads more often and for longer. Colonies of bats resting in bridges startle at irregular bangs and clanks. Small mammals that use sound to keep track of companions or to scan for predators find their signals masked. They raise their own volume or call more often, and rest slides further away. Human presence is its own soundscape. Dog walkers, cyclists, joggers with headlamps, night anglers, drone hobbyists, all can pass a sleeping animal's threshold for safety without meaning to. The response might be a flush from a roost, a sprint from cover, or simply a shift in posture and a long minute of stillness that pushes the sleeper back into shallow stages. When these arousals repeat, the costs accumulate. Tougher mornings, slower reaction times, choices made with foggier minds. Multiply that across a nesting season or a migration, and the arithmetic tilts against survival. What does chronic sleep loss look like in the wild? It is not a drooping eyelid and a cup of coffee. It is a blackbird that misjudges a rival's intent and wastes energy on a fight. A bat that leaves the roost too early and meets a hawk in the last light. A deer that chooses a bedding site for quiet but not for cover because the brain is answering the wrong question. The body keeps trying to compensate. Some species nap more by day, some shift their foraging hours, some retreat to smaller home ranges that feel predictable. Those workarounds carry their own costs, less time in the best feeding patches, more competition with neighbours, and, in crowded places, a higher chance of conflict with people. The good news is that sleep is not just vulnerable, it is recoverable, and small changes help quickly. Shielding light so they shine down, not out or up, preserves darkness beyond the target area and restores stars to a sky that animals use for orientation. Choosing warmer, amber tones reduces the blue that most powerfully shifts biological clocks. Motion sensors and dimmers let a path stay dark until feet actually arrive, cutting hours of needless glow. Curfews for decorative lighting buy back deep night, the hours where melatonin rises highest and rest runs deepest. During migration, voluntary lights-out policies dim towers and stadiums for a handful of crucial weeks, and millions of wings pass over a darker, safer city. Quiet can be designed too. Lower speed limits and softer road surfaces shave the constant hiss. Vegetation belts and earthen berms along park edges muffle human noise before it reaches roosts and dens. In urban parks and coastal refuges, setting aside true night hours, no drones, no amplified music, no off-trail wandering, gives the creatures tucked into reeds, rock, and root the confidence to drop into deeper stages. Where recreation must go on, concentrating activity into predictable windows helps wildlife learn when the world will be calm. Conserving sleep does not always sound heroic, but its dividends reach into every corner of conservation. A bird that sleeps well learns a route and keeps it. A bat that sleeps well nurses a heavier pup. A fox that sleeps well wakes sharp and hunts with fewer mistakes. Whole populations become more resilient when nights are dark enough and quiet enough to let those small advantages stack. Corridors of darkness link roost to river and marsh to wood, letting animals move without crossing a glare. Dark sky parks and reserves protect more than stargazing. They protect the biology of night. In the end, the cure for the sleep-deprived wild is humble. Give back the dark and give back the hush. Let the city keep its light where it needs it, on the step, on the path, on the ball, and nowhere else. Let the loudest hours be short and expected. If we can make those choices, owls will blink slower, bats will tuck deeper, frogs will spend a little more of the small hours in true quiet, and dawn will find the wild part of town better rested for the day ahead. Some corners of sleep science look like stage magic. Pigeons wearing tiny headsets, seals mailing data from the middle of nowhere, and octopuses that change colour while they doze. The tricks are real, the props are careful, and the reveals teach us how flexible sleep can be when life insists on odd hours and odder places. Start with the pigeon in a snug cap. Birds have thin skulls and lightweight bodies, so researchers build featherweight electroencephalography rigs that record brainwaves without tipping a perch. A few miniature electrodes rest on the skull just under the skin, glued in place and linked by fine wires to a backpack the bird barely notices after a short acclimation. What those squiggles show is familiar and strange at once. Pigeons slip between slow, rolling waves that mark deeper, non-rapid eye movement sleep, and faster, desynchronized patterns more like wakefulness. Short bursts of rapid eye movement appear in seconds-long flashes. In a quiet loft with trusted flockmates, the night settles into tidy cycles. In a new room or near a window that catches streetlight, the record fragments, more brief arousals, more one-eyed dozing, less time in the deepest, most restorative phase. That one-eyed look is not a party trick. Like many birds, pigeons can give one hemisphere of the brain a nap while the other keeps watch. The open eye faces the potential trouble, the closed eye faces the wall. Put a row of birds on a perch and the ones at the ends tend to keep their outward eye open more often, while those in the centre melt into fuller, bilaterally sleeping bouts. The headgear makes the pattern visible. On the guard side, brainwaves stay brisk. On the other, slow waves rise and fall like a tide. Rotate the row, and the guard eyes rotate with it. The lesson is both simple and generous. Safety is shared, and with it, real sleep. Now shift to a seal at sea. You cannot ask it to hold still for a bedtime recording, so the lab follows along with a stack of clever tags. A location transmitter pings satellites each time the seal surfaces. Time-depth recorders log dives as elegant traces. Accelerometers feel posture and flipper beats. Stitch those together, and an underwater sleep diary appears. Northern elephant seals are champions of the micronap. At sea, they descend into drift dives, stop stroking, and let the ocean carry them while the body goes limp. The accelerometer tilts as the seal rolls. The depth trace smooths. Brief bursts of motion return as the animal rouses to steer and breathe. Add up the minutes across a busy foraging night and total sleep time can be astonishingly small, yet enough to keep cognition and reflexes working between hunts. Fur seals reveal another trick. On land, they sleep like typical mammals, both hemispheres off together. At sea, vigilance and breathing demand a compromise, and the tags catch it. One half of the brain sleeps while the other keeps the stroke slow and the head angled toward air. In heavy swell or noisy shipping lanes, bouts shrink. In quiet currents, they lengthen. Because the devices record for weeks, patterns emerge that a one-night observation would miss. A rough patch of weather echoes in thinner sleep for days. A stretch of calm brings a rebound into deeper, longer bouts. The ocean also hosts a sleeper whose dreams, if they are dreams, show on the outside. In darkened aquariums, high-sensitivity cameras watch octopuses and cuttlefish through the small hours. Most of the time, their skin rests at a low-effort tone. Mottled neutrals, breathing steady, pupils narrow slits. Then a minute arrives that looks like a memory unspooling. The mantle ripples with high contrast bars, cheeks flare pale, arms curl and stretch. A wave of dark travels the body like a storm front. The sequence lasts a handful of heartbeats and fades. A while later, another arrives, different but composed from the same alphabet of patterns the animal uses while hunting and hiding by day. Is the cephalopod dreaming? The cautious answer is that its brain is in an active sleep state reminiscent of the phase in which mammals and birds so often report dreams. In that state, internal activity may recruit the colour-changing system that, in waking life, serves camouflage and communication. Because chromatophores are muscles, a brief burst may also act as maintenance, a coordinated flex that keeps the system responsive. To avoid wishful thinking, researchers pair the videos with measures of arousal threshold and rebound after mild sleep loss. The animals are harder to rouse during quiet stretches, easier during active ones, and, if disturbed through the night, show longer, deeper quiescence the following day. Whatever the colours mean, the package of signs fits a real, regulated sleep. Behind each odd contraption sits a stack of ethical choices. A good wildlife tag is a negotiation. It must be small enough to disappear into an animal's life, robust enough to ride out storms, and informative enough to justify its presence. For birds, the rule of thumb is to keep gear well under a few % of body mass, and shaped to hug the body so it does not foul feathers or flight. For marine mammals, hydrodynamics matters as much as weight. Any proud edge can cost energy in a long migration. Many tags now release on a timer or at the molt and float to the surface to upload their data, sparing researchers the stress of recapture. In the lab, the ethics are different but just as real. Placing electrodes means anesthesia, and that means a careful protocol and quick clean surgery performed by trained hands. Housing must deliver darkness that is truly dark to a bird's eyes, not just to ours. Water quality and tank design for cephalopods need to support exploration and den building, because a cramped, bored animal does not sleep like a wild one. When a study is over, the question becomes what justice looks like for an animal that played its part. Release where appropriate, adoption to enriched facilities where possible, and always a sober accounting of what was learned relative to what was asked of the subject. There is also the ethics of the question itself. Some sleep studies can be done with passive recordings and patient observation. Others tempt with experiments that tug hard on stress and deprivation. The field has shifted toward gentler designs, shorter disturbances, subtler manipulations, and more respect for natural schedules. New tools help. Better cameras and microphones let researchers collect rich data without touching a sleeper. Machine learning can find the signature of a nap in a river of sensor noise. With each generation of gear, fewer animals carry gadgets, and those that do carry lighter ones for less time. What makes these experiments weird is not only the sight of a pigeon in a bonnet or a seal with a satellite link. It is that sleep, which feels private and delicate, keeps turning out to be rugged and ingenious. A brain can rest in halves and in slivers. A body can nap while sinking. A skin can tell a story in the dark. The ingenuity of the methods mirrors the ingenuity of the sleepers, and when the two meet well, with care, with restraint, and with designs that vanish into ordinary behaviour, the payoff is a clearer picture of how life keeps its edge sharp by laying it down for a while. If there is a final rule in this odd toolkit, it is this: disturb as little as possible, learn as much as you can, and let the animal go back to being the expert. The pigeon will keep its watch with one bright eye. The seal will fold into the ocean's slow elevator and take a drifting minute. The octopus will paint a brief mural that no one sees. We get a glimpse, write it down, and dim the lights. Sleep seems effortless until it is not. Most animals slip through clean cycles of quiet non-REM and vivid REM, waking ready for the next round of living. But every now and then, the machinery misfires. Paws paddle across floors, tails thump erratically, eyes snap open to nothing at all, and a night meant for repair becomes a tangle of confused motion. When sleep goes wrong in animals, the clues are often dramatic, and teasing apart what is harmless from what needs help starts with knowing the difference between dream twitches, true sleepwalking, and a disorder that lets dreams spill into the body. Pet owners often say their dog or cat sleepwalks, but most of what looks like nighttime wandering is not classic sleepwalking. True sleepwalking, somnambulism, arises from deep non-REM sleep. The brain is partly offline, awareness is low, and movements are automatic and aimless. In people, that can mean walking and opening doors. In animals, it is rarer and harder to confirm because we cannot interview the walker afterwards, and because plenty of normal behaviours can mimic it. Puppies and kittens twitch, paddle and chirp during REM. That is ordinary motor play from a dreaming brain. Older animals may pace at night from pain, itching, or anxiety and look asleep simply because the lights are off. Seizures can also resemble sleepwalking to an untrained eye, a stiff, entrained rhythm, sometimes followed by disorientation. True somnambulism in dogs and cats appears to be uncommon, and when it is reported, veterinarians look carefully for pain, neurological disease, medication effects, or cognitive decline as more likely explanations. A different problem is both better documented and more dramatic: REM behaviour disorder. In healthy REM, the brain is busy but the body is safely still. A brainstem circuit switches on muscle atonia, a protective paralysis that keeps dream movements from reaching the limbs. If that circuit fails, the sleeper can act out dreams. In dogs, that may look like snapping at imagined prey, galloping from a dead sleep, or leaping up and colliding with furniture. In cats, episodes can include stalking motions, batting at phantoms, or sudden defensive swats. The animal often wakes quickly and looks alert and confused, as if the movie in its head suddenly dissolved into the room. Because REM behaviour disorder comes from a specific failure to maintain atonia, it tends to follow a pattern. Episodes are tied to REM-heavy parts of the night. They stop as soon as the animal is fully awake, and neurological exams between events can be entirely normal. In people, the condition can be a warning sign of future neurodegenerative disease. In animals, the long-term links are less clear, but age and underlying brain illness can play a role. In the clinical world, veterinarians focus first on safety: soft bedding, blocked stairs, moving fragile objects, and then on causes and management. Some cases quiet with changes to evening routines and stress load. Some respond to medication under veterinary guidance. The important distinction for owners is this: vigorous, purposeful-looking behaviour in deep sleep is much more likely to be REM behaviour disorder than sleepwalking. Do wild animals develop REM behaviour disorder? It is a difficult question to answer. Confirming it requires measuring brain waves and muscle tone, which is hard to do in free-living creatures. Most field evidence is indirect. Camera traps that catch a fox thrashing in its den, or keeper's notes on zoo animals that act out dreams during rest. Marine mammals, which often rely on unihemispheric sleep, complicate things because atonia is already minimal during their typical rest. Birds add another wrinkle. Bilaterally sleeping pigeons and one-eyed ducks can show complex movements without ever being in classic REM paralysis. The best we can say is that dream enactment-like episodes do occur across species, especially under captivity stress or illness, but rigorous diagnoses outside clinical settings remain rare. Then there is insomnia, not a single disease, but a family of problems where sleep is too short, too shallow, or too broken to do its job. In pets, the common culprits are practical. Pain is high on the list. Arthritis, dental disease, and post-surgery discomfort push animals to pace and reposition through the night. Itch is another. Allergies, fleas, and skin infections can keep a dog or cat in a cycle of scratching and waking. Anxiety matters. Thunderstorms, fireworks, and separation worries fragment sleep into little shards. In older dogs, cognitive dysfunction, the canine relative of human dementia, can scramble circadian timing. Night becomes day, wandering replaces rest. Confused vocalizations wake households at odd hours. Endocrine diseases, digestive upset, and certain medications also erode sleep by stoking thirst, urgency, or restlessness. Wild animals face their own set of insomnias. Artificial light at night suppresses melatonin, shifts clock timing, and keeps birds, bats, and insects active when their biology expects quiet. Urban noise sprinkles a night with unpredictable spikes that drag sleepers back to the surface. Heat waves force panting and open-mouthed breathing that interrupt rest. Drought drives longer, riskier searches for water. Predation risk trims sleep by design. A deer on an open verge will choose many light microrests over a few deep ones, but human disturbance piles on additional arousals. A dog off-leash, a cyclist at dusk, a drone overhead. Parasites turn dens and nests itchy. Cramped conditions in recovery enclosures can make deep sleep feel unsafe. In all these cases, the behaviour labelled insomnia is often an animal doing its best with a bad hand. The thread that runs through these disorders is cost. Poor sleep does not just feel unpleasant, it blunts reflexes, muddies decisions and dulls learning. A dog that slept badly after fireworks may be irritable at the park. A cat with nocturnal pacing will nap the day away, missing play that keeps weight and mood in balance. A wild bird short of deep rest navigates a little less precisely and risks more collisions. The fix is rarely one silver bullet, but small practical shifts add up. In homes, treat pain and itch, keep evenings calm and predictable, darken and quieten the sleeping space, and give older animals steady light cues to anchor their clocks. In shared landscapes, dim lights, shield them downward, keep true quiet hours, and design hideaways where a creature can believe it is safe enough to let go. Most of the time, sleep works beautifully. When it does not, animals tell us with paws and wings and eyes that refuse to stay closed. Listening, with curiosity first, and then with a willingness to change the room, the routine, or the rules, is often enough to turn a troubled night back into the ordinary miracle it should be. The next decade of sleep science looks less like a lab with a single wire, and more like a quiet orchestra of tools that can listen to the brain without breaking the spell of rest. Some advances feel almost like magic. Tiny microscopes, miniscopes, can now ride on the heads of freely moving mice and birds, recording the flicker of calcium in neurons as they drift through non-REM and burst into REM. 2-photon imaging once needed animals fixed under a lens. Clever head mounts and lighter optics are bringing more natural postures and longer recordings. Functional ultrasound, which reads blood flow changes with astonishing sensitivity, can track slow waves rolling across deep brain structures through a small window in the skull, with less noise and bulk than older methods. On the electrical side, paper-thin electrode arrays and neuropixels probes capture activity from hundreds of neurons at once, revealing how sleep spindles, slow oscillations, and rapid eye movement bursts stitch together across circuits. None of these tools is perfect, but together they let researchers watch sleep not just as a global state, but as a conversation between brain areas. Imaging is also leaving the bench. Magnetic resonance scanners have been tuned for quieter gradients and dimmer lights, allowing natural sleep in humans and in specialized setups in larger animals that tolerate short, calm sessions. Near-infrared spectroscopy offers a portable, light-based view of blood oxygen, changes in cortex, useful for animals and people who cannot set foot in a scanner. Even the humble EEG is evolving. Flexible, wireless caps record brainwaves across whole nights without tethers, and gel-free electrodes make it practical to study sleep in species that would never accept a messy setup. Out in the field, artificial intelligence is doing what no graduate student can, watching, listening, and scoring around the clock. Accelerometer biologgers, matchbox-sized motion sensors glued to feathers, fur, or collars, have been used for years, but the flood of data they produce is now decoded by models trained to recognize the signature of a micronap on a drifting seal, or the one-eyed doze of a duck at the edge of a flock. GPS tracks overlay those states on maps, so researchers can ask where animals sleep, not just when. On cliffs, camera traps and thermal images paired with computer vision can tell if a kittiwake is incubating, preening, or deeply asleep, even in the wind. In forests, arrays of tiny microphones feed algorithms that distinguish the lull of normal colony chatter from the alarm that fragments rest. Edge computing, doing the analysis on the tag itself, is the next quiet revolution. A bat-borne device can classify glide asleep versus glide awake in real time and decide to store high-resolution data only when something interesting happens, extending battery life from days to weeks. On coral reefs, low-light cameras watch octopuses through the night. Software finds the brief, high-contrast flares of active sleep and marks them for closer study. In labs, unsupervised learning sifts through EEG and calcium traces, discovering sleep microstates that do not fit neat textbook categories. These data-driven maps already suggest that REM and non-REM are umbrellas, shading many distinct patterns that species mix and match to suit their lives. With power comes questions. The ethics of sleep research used to focus on deprivation. How much is too much? And what is the scientific value of pushing an animal beyond its normal limits? That debate has shifted toward gentler designs, but new dilemmas arrive with the hardware. A tag that weighs a few grams can still matter to a small bird. Added drag on a diving seal is a tax paid every minute. A head-mounted scope changes how an animal moves through its world. Good practice means strict limits on device mass, smooth shapes that do not snag, short deployments, and automatic releases that drop a tag without recapture. It means measuring not only the data we want, but also the cost we imposed: flight speed, dive efficiency, grooming time, and publishing those costs openly so the field learns. Captive studies raise their own issues. Sleep is exquisitely sensitive to context. A tank too small for den building, a terrarium without a true dark or a noisy corridor, can bend behaviour into something that looks like a result but is really a response to an artificial world. Reform here looks practical. Larger, more natural enclosures, true darkness at night for eyes that see more of the spectrum than ours, social housing for social species, and patience to let animals learn a routine before recordings begin. Cephalopods and decapods are now widely recognised as sentient in many jurisdictions, which brings new welfare standards to experiments that once treated them as simple. The same principle applies everywhere. Refine the method until the animal can sleep the way it would choose to sleep. There is also a question of place. Wild studies feel real, but they can be invasive. Captive studies feel controlled, but they can be misleading. The best work combines both. Lab tools discover a mechanism, a brainstem circuit that gates atonia, or a thalamic rhythm that boosts memory, and field tools ask where and when nature uses it. Conservation folds in when we recognise that protecting sleep is part of protecting habitat. A dark corridor that links roost to river is as important as the roost itself. Quiet hours in urban parks can matter as much as acreage. If we can measure sleep well, we can defend it with confidence and design cities that let animals switch off fully when night should be night. The future then is less about ever stranger gadgets and more about gentler ones that vanish into ordinary life, sensors that listen without tugging, cameras that see without blinding, algorithms that learn patterns without demanding that animals perform. Add to that a culture that prizes the 3 Rs: replace, reduce, refine, and treats sleep not as a resource to be mined, but as a living process to be observed with care. When those pieces align, we will read the brain's nighttime stories with far more clarity and far less intrusion, and we will be better stewards of the darkness all sleepers need. Night moves like a slow tide around the planet, and life moves with it. In a rainforest, twilight folds into the canopy, and the last shafts of sun thin to green smoke. Birds settle on hidden perches, some tucking one foot into feathers, some lowering a third eyelid that acts like a soft curtain. Fruit bats leave their roosts in the wafers of shadow, and beneath them, leaf-cutter ants dim their rush to a quiet trickle. Tree frogs find still places on broad leaves. Monkeys curl tails around branches, breathing in unison, the whole forest exhaling together as darkness takes its turn. Across a desert, Heat drifts up off sand like a memory that refuses to fade, then slips away all at once. Daytime lizards have already chosen crevices that keep the night's chill at arm's length. Fennec foxes fold themselves into shallow scrapes, where warm earth and starlight meet. Tiny gerbils punctuate the quiet with small rushes to seed caches before returning to safety and short, light rests. Some plants close their flowers, some open theirs for nocturnal pollinators. Life here rests in sips, because the desert writes its rules in extremes and asks every creature to answer with care. On polar ice, the season decides what night means. In the long winter, darkness lingers for weeks and the cold is a clean knife. Emperor penguins hold eggs like promises, passing them foot to foot within a huddle that moves as slowly as a glacier. The interior sleeps warmer and deeper while the edge keeps the wind honest. A living rotation of sentinels and sleepers. Far offshore, seals bob like punctuation marks in black water, surfacing at patient intervals from drift dives taken in the sea's cold cradle. In summer, the sun skims the horizon and refuses to set. Sleep shifts into fragments that follow the body's clock rather than the sky's. Grasslands carry their own choreography. Herds choose bedding sites that catch a breeze and offer a view. Individuals relax in waves. A ribbon of heads lowers, another rises. Owls take the night shift and lions decide whether hunger or full bellies rule the hours. Small antelope fold their legs, sleep lightly, and answer every rustle with a listening pause. The prairie's soundtrack is not silence so much as pattern. Crickets, a distant jackal, the wind-combing seed heads, and brains tuned by evolution treat that pattern as a lullaby, waking only when the rhythm breaks. Under mountains, a river keeps time without caring whether it is day. Trout slide into eddies and hold position with tiny fin beats, letting metabolism slow as darkness cools the water. On ledges far above, goats and sheep find night shelves that rock less in wind. Bats ripple from cave mouths at dusk, then return in a soft rain just before dawn, folding into clusters that share warmth and carve out narrow hours for deep rest. The alpine night is thin but not empty. It is simply careful with its energy, and so are the sleepers who live there. Down in the deep ocean, where noon is a rumour, sleep adopts new shapes. Some fish press close to the seabed and pale to match it. Others hover and trust the slow muscles of station-keeping to hold them. Octopuses wedge into rock cracks and at intervals let their skin tell brief stories of patterns that might be memories. Whales descend into slow, idling spirals or float, as if the sea were holding them in a great palm. The deep does not do hurry, and its sleepers obey. The loudest thing is the absence of light, and many bodies answer by dimming their own. These nights are not separate events. They are strands of the same braid. The planet's rotation sets a daily beat that reaches every cell with an internal clock. Tides tug at coastal sleepers with second rhythm asking shore crabs and seabirds to fit naps between waters in and out. The moon writes a longer line. Hatchlings and migrating fish heed it. Predators learn it. Reefs glow a little different under it. Seasons stretch and compress darkness at the poles and tease it at the equator, bending sleep's schedule without breaking its purpose. A bat's fragment of rest in a city park, a penguin's micro-sleep in a huddle, and a parrotfish's pastel night colours are all replies to the same cue, not yet day. The threads cross in ways that make the world feel smaller. Bats that forage by night pollinate cacti whose flowers open only in darkness, which feeds hawk moths that sleep by day in shaded stone. Shorebirds timing their migrations to the moon and tide arrive in Arctic summer that offers rest in slivers, and they carry that borrowed rhythm back across hemispheres when they go. City lights hold swifts awake longer. Their fatigue changes when and where they feed. The insects they miss lay eggs that hatch, to feed the chicks of another species on another schedule. Sleep cycles are not just private stories. They are traffic rules for energy moving through ecosystems, everywhere, Sleep is a difference in degree, not an on or off. A duck at the edge of a raft keeps one eye open while the centre of the flock dreams. A dolphin lets one hemisphere drift while the other steers. A giraffe makes do with minutes and still wakes ready to run. The details change with habitat and history, but the reason holds steady. Sleep is the nightly maintenance of bodies that must last. A fresh coat of clarity on memory, a reset of immune watchfulness, a sweep of chemical housekeeping. It is vulnerability managed by design, traded for a morning that works. If you listen now, or to your own breath, to the room, you might notice that your rhythms have been joining the planets as we travelled. Words slow, images soften. Somewhere a rainforest is settling, a desert is cooling, ice is tightening its grip, and the deep sea is turning pages you cannot see. Somewhere you are in that map, a sleeper among sleepers, sharing the same old contract with the dark. If your eyes are heavy, let them close. The world will keep its watch, and morning will find you where it finds everything else, rested enough to begin again. We have wandered through a world where sleep wears many faces. We met the gentle architecture of non-REM and the vivid theatre of REM, then watched dolphins and birds divide the night between their two hemispheres, keeping one eye open on the dark. We saw masters of the micronap take rest in thimblefuls, and nearly sleepless giants, giraffes and elephants, make do with minutes. Dreams flickered in kennel twitches and in the colour stories of cuttlefish and octopuses. Flamingos balanced on a single leg. Bats trusted tendon locks to hang upside down. Sloths turned tree crowns into hammocks. Winter taught us the difference between long hibernation and quick torpor, while reefs, rivers and open seas showed how to sleep underwater without eyelids, or even without a brain, as jellyfish settled into true quiescence. Insects drooped their antennae. Prey slept lightly in exposed places. Noisy nights became lullabies of predictability, and families huddled for warmth and safety. Parents traded deep sleep for vigilance. Cities rewrote darkness with light and sound, and we learned how a few wiser choices can give night back. Curious tools, tiny headsets, satellite tags, soft cameras, open doors, and an ethical compass reminded us to knock gently. Finally, we stepped back to watch the planet breathe, a rolling tide of rest circling forests, deserts, ice, and deep ocean. Why does any of this matter? Because sleep is not a luxury tacked onto life. It is part of how life works. When an animal rests well, it remembers roots, fights infections, heals small injuries, and wakes with sharper decisions. Protecting sleep protects behaviour we care about. Migrations that arrive on time, parents that raise more young, pollinators that find the right flowers, predators that hunt cleanly, and communities that waste less energy on mistakes. Understanding sleep also sharpens our empathy. A bat avoiding a streetlight, a penguin rotating through the huddle, a deer stacking micro-rests at the field's edge, each is solving a problem. When we dim lights, keep true quiet hours, and leave threads of habitat unbroken, we are not indulging a whim. We are repairing the conditions that let those solutions work. There is wonder too, knowing that a jellyfish without a brain still needs rest, that a duck can sleep with one eye open, that an octopus might wear a brief mural of a dream. These facts make the night feel richer. They remind us we share an old contract with darkness. Give the body a spell of safety, and it will repay you with a brighter morning. If your eyes feel heavy now, that is perfectly fine. Let the details blur and keep only the feeling that the living world is very good at taking care of itself when we let it. Thank you for drifting through these chapters with me. And if you made it through all 22 chapters without nodding off, you may be part giraffe, in which case, congratulations on your impeccable vigilance, and good night all the same.